Good morning, everyone. We'll give one more minute for the folks to keep chiming in, and then we'll get started so we can stay on track. Some of us were up early for the breakout sessions that started an hour ago. That was very vibrant and fun. So for those of you who were there, thank you for joining. All right, let's get started. Oh, someone want to say something? All right, well, everyone, welcome to day 2 of the Star Planets and the Ultraviolet Cross-Community Symposium. I hope you guys enjoyed yesterday, and I certainly did, and I learned a lot. So I'm just going to keep it very brief, but I do want to remind all of you about our Zoom etiquette for the day. Also, because I know some of you weren't with us yesterday morning, so I'm just going to repeat this. So please mute yourself when not speaking, which is, I think, obvious, and you guys were really great about it yesterday, so thank you very much. Also, please unmute yourself to clap after the talks. It's just nice for the speakers who put so much work into it to know that there are all these people listening and watching and paying attention. And also unmute yourself and turn on your video if you like to ask a question. To ask a question, please raise your hand using there was some confusion yesterday that you have the reactions at the bottom of your screen. If you click that, there's a hand raise option and a lower hand option. So please use that, and our chair will go down the list. And if we run out of time for questions, just type them into the chat and the speaker will address them there. Okay, either privately or publicly in the chat for that. And then we do have, just as a reminder, multiple ways to engage, and people have really been using this in a really fun way, so I'm so delighted. We have Gather Town set up for this meeting, where there's a coffee shop with games, and of course the poster room, and that's where all the posters are. And in the poster room, you can go watch all the poster pops also that we saw a few yesterday, and we'll see a few more today. And they're all still recorded there, so you can go watch and rewatch them if you happen to miss it. And lastly, the third way we've been interacting is through these breakout discussion questions, where we talk about the top 10 big questions as voted on by you guys, those of you who participated in the voting system. We already started earlier this morning at 8 o'clock Pacific time and had some great conversations. And there's 2 more of these breakout discussions happening for the conference, one today, this afternoon here at 12:55 Pacific time, and then tomorrow morning, again at 8 o'clock Pacific time, and the questions are listed here for you to read. They are also on the agenda in one of the spreadsheets. If you look at your ultimate guide to the Star and Planet Ultraviolet Conference meeting guide, as we put it, into your email, it's all there. So please click on all those links. You'll find all the questions that are going to be discussed in these breakout sessions, and it's been going really smoothly and really interactive, and by all means come and join the fun there. So I'm going to stop sharing now. Thank you again to everyone for coming. Thank you to all our speakers for making this really interesting, and thank you to Josh Lothringer, who's agreed to chair this session. So I'm going to pass it over to Josh now. Thank you.
Awesome. Well, hello everybody. Good morning. So we're going to get started with our first session of the day on exoplanet atmospheric escape. I'm Josh Lothringer. I'm a postdoc at Johns Hopkins University. And let's just get started with our first talk by James Owen from Imperial College London. If you want to go ahead and share your screen, who will be talking about a review talk on the role of atmospheric escape. So take it away. I don't believe we can hear you, James. Yeah, we still can't hear you, James. Can you hear us? Let's see. It looks like you're unmuted, which is weird.
If you go to the bottom of your screen where it has the mute button and it has an up arrow, you can check what speaker and microphone you're using.
How is that? Excellent.
Yes, we can hear you.
No, yeah, it has selected the wrong microphone, unfortunately. Great, well, let's start again. So it is a great pleasure to be able to give this talk to you on this burgeoning topic of atmospheric escape that's become particularly important in the context of all these thousands and thousands of close-in exoplanets we've been talking about. And you're going to hear many, many talks about this topic throughout the rest of this session. So I'm going to highlight the talk of my PhD student in the next talk, James Rogers. Ruth Murray Clay is also going to give us a talk on atmospheric escape. And we're going to hear about this new MIDEX mission concept UV scope that I'll touch on right at the end of my talk. So why is atmospheric escape or mass loss from exoplanets becoming particularly important? So as I said, we've been finding thousands and thousands of exoplanets. So this is just a census of exoplanets. And what I'm showing is their irradiation levels in units of Earth flux. So the Earth is sort of 1 back here. And their radius scaled to the radius they would have if, given their mass, they were composed of an Earth-like material. So if they were completely rocky, they would have a radius that sits along this line here. So the Earth sits somewhere down here. This blue line is what you would be composed of if you were sort of a classic 100% water world. And what you can see is there are many planets that extend way above these lines. And the only way we know to make planets this large compared to their rocky mass they might have is to add lots and lots of hydrogen and helium to these planets. So the other intriguing thing you see is that the amount or size of these planets, hydrogen and helium atmospheres, gets smaller as you go to higher and higher irradiation levels. So the classic explanation for these planets and this trend is that you have planets with large hydrogen and helium atmospheres that are exposed to UV radiation from the central star, and that UV radiation drives powerful hydrodynamic outflows that cause the planets to lose mass over their billion-year lifetimes. So if we think about this more quantitatively at the population level, what we can do is we can think of planets at birth that have a solid core that is composed of rock, iron, ice, maybe, surrounded by hydrogen helium atmosphere. And then we can let the star bombard these hydrogen helium atmospheres with UV photons and drive these powerful hydrodynamic winds that cause planets to lose mass over their billion years lifetimes. And what we find is that planets that are close to their stars or planets that have really small cores tend to completely lose their hydrogen helium atmospheres and get completely stripped. And planets that are a bit further out or planets that have very large solid cores tend to retain something like 1% of their mass in hydrogen helium. And if we think about what this gives us in the radius period plane for the population of exoplanets, we end up with this bimodal population of exoplanets. So planets dominated by 2.5 Earth radii. These are the planets that in the models are retaining about 1% of their atmosphere by hydrogen helium, and planets that have completely lost their hydrogen helium atmospheres, these stripped cores, and this is separated by a gap or an evaporation valley. Now, one of the interesting questions you should ask yourself is, this mass loss process looks like this quite continuous process. Why on earth does it give us this distinct bimodal exoplanet distribution in radius? And it's actually quite easy to understand. It's easy to understand if you consider the mass loss timescale of one of these atmospheres as a function of how we grow the atmosphere. And what the mass loss rate is set by fundamentally is two specific quantities: how deep a gravitational potential well you have to escape from, and how much high energy flux you can absorb from the star, basically how big a planet's radius you have. So you can envisage if you take a solid core and you add a tiny veneer of atmosphere and add a tiny veneer of atmosphere again, you haven't changed the planet's mass by very much, and you haven't changed the planet's radius by very much. So you haven't changed the mass loss rate, but you've added material to the atmosphere to lose. So that means that for very small mass loss envelope masses, the mass loss timescale is going to increase. It's going to get harder and harder to lose an atmosphere as you add more mass. But eventually, you're going to reach the point where the atmosphere, the hydrogen-helium atmosphere, is so thick, it now dominates the radius of the planet. And now what matters for the mass loss timescale, right, is how quickly your planet blows up as you add hydrogen-helium. Hydrogen-helium is a really light gas, has a high, low mean molecular weight, large scale height, so it blows up really quickly as you add a tiny amount of hydrogen-helium. So it turns out that the mass loss timescale turns over, and it turns over naturally at the point where your atmosphere has enough mass that it can double the course radius. So now we can take this diagram and we can make it in a slightly more scientific sense, and we can put some units on here. So we have our mass loss timescale as a function of envelope mass fraction here. You tend to peak here, you double the course radius at about 1%. So this means that any planet structure that has a mass loss timescale less than the time in which we have to lose our atmospheres. So this is typically the timescale on which stars are X-ray and UV bright. So something like 100 million years for main sequence sun-like stars. Sun-like stars. Then any planet that has any planet structure that has a mass loss timescale less than 100 million years is going to be unstable to mass loss, and it's going to move this way in the diagram. And any planet that has an envelope that is has a mass loss timescale longer than 100 million years is going to be stable to mass loss, and it's not really going to evolve in this plane. So what we can do is we can take two initial conditions. We can take a planet with a large amount of hydrogen helium that's far away from the core, so its initial structure might still be unstable to mass loss. And then you can take a different structure. You can take a planet that's a bit close to the star and has much less hydrogen helium to start with, and you can consider how these planets are going to evolve in this plane. Right. They're both unstable to mass loss, so they're both going to lose envelope mass, but this planet is going to evolve to a stable region where its mass loss timescale grows, whereas this planet here is completely stripped. As you start losing a bit of atmosphere, it completely runs away. So this is why you get this bimodal nature. You either pile planets up here at the point you're most stable to mass loss, or you completely strip them. So this bimodal nature is actually a natural outcome of this mass loss process, even though naively it's seemingly that it might not. So this gives us planets with a 1% hydrogen helium atmosphere, or these stripped cores. Now we can fit this exoplanet distribution beautifully with the evaporation model, but I'm not going to talk about that because in the next talk you're going to hear from my PhD student James Rogers, who's going to tell us all about this. And actually, given your final outcome is set by your initial conditions, he's going to tell us how you can back out the initial conditions, which is really exciting. But the thing I want to highlight is perhaps that because these planets are starting off with a large hydrogen helium atmosphere that we're then stripping, we now have a new way, a new pathway to form terrestrial planets that's somewhat distinct from perhaps how the terrestrial planets formed in our solar system, where they didn't start off with something like 10 or 20% of their mass by hydrogen helium. So planets are going to form their heavy element or secondary atmospheres either by outgassing and then some subsequent mass loss, or in this new pathway, you're going to lose your hydrogen helium atmosphere while perhaps you're outgassing as well. And the final outcome of what you end up in your terrestrial planet atmosphere may be distinctly different from this second pathway. So one of the things we're thinking of in my group is extending these mass loss models, not just to hydrogen helium mass loss, but to secondary atmospheres as well. So I'd encourage you to look at two posters from Matthias and from Laura. Matthias is looking at what happens at the transition between hydrogen-dominated atmospheres and heavy element-dominated atmospheres. And Laura's looking at how hydrogen escape can drag along heavier elements and change the composition of our exoplanet atmospheres. So take a look at these posters. It's really sort of cutting edge stuff, and it's really important for what we're going to be discussing in terms of what we think is going on in terrestrial planets later on. But the thing I think I want to highlight is that anything that I tell you, James is about to tell you, Matthias or Laura will tell you, or anyone else is going to tell you, depends on the accuracy of these mass loss models. And at the moment, these mass loss models are yet to be directly and quantitatively calibrated against observations. And this is really important because hopefully I've convinced you that this atmospheric escape process is really important, but at the moment you just have to trust us on that our models are really good or really bad. So we want to observationally probe this mass loss, and we have an excellent way of seeing whether a planet is undergoing atmospheric escape, and that is through transmission spectroscopy in Lyman-alpha. So what I'm showing here is the Lyman-alpha line of the star GJ436b. These top two black and blue lines are showing the Lyman-alpha line we observed for the star while the planet is not transiting the star, but the green and the red line are showing the transit when the planet is transiting the star. And we get this huge 50% dip, right? We're blocking 50% of the star in Lyman-alpha when the planet is transiting. Lyman-alpha is extremely sensitive to neutral hydrogen. This transit also lasts a really long time, so it's really deep and it's really long. It can last 10, 20 hours for GJ436b. This is the optical transit here. So we're blocking an enormous amount of the star. And the picture we have in our mind is that we have a planet that's undergoing atmospheric escape. It's blowing neutral hydrogen off it, and we're blocking Lyman-alpha from the star by absorbing the stellar Lyman-alpha line in this neutral hydrogen tail. But there's a bit of a sort of unusual nature about the Lyman-alpha transits, and it's a bit sort of difficult to interpret in terms of quantitatively testing the mass loss models. So sometimes you see whopping Lyman-alpha transits, like this GJ436b one I was just saying, where you see a 50% reduction. But for this other seemingly similar planet, HD 97658b, you see no evidence of a Lyman-alpha transit. And what's even more naively confusing is that this planet here is even more highly irradiated than this planet. So this might tell you, well, if this planet's more highly irradiated, shouldn't it be undergoing more vigorous mass? So why you sometimes see and sometimes you don't see Lyman-alpha transits is part of the mystery. So in order to answer this question, what I'm going to talk about is sort of going back to basics and trying to understand the basic physics of atmospheric escape and the basic physics of Lyman-alpha transits and seeing what that's telling us. So we're going to take that cartoony picture of what we just said and we're going to build on that. So we're going to envisage our planet that's orbiting our star, and it's losing mass and creating this sort of cometary tail behind it in some outflow. And we're seeing a Lyman-alpha transit when this cometary tail is transiting in front of the star. And one of the curious aspects about the Lyman-alpha transit is because of ISM absorption, we can only probe the line wings. So something must be accelerating this cometary tail radially towards the observer so that we can actually see the Lyman-alpha transit at hundreds of kilometers per second. Right? Atmospheric escape models do not predict that you're blowing material off the planet at hundreds of kilometers per second, more like 10 or 5 kilometers per second. And thanks. And any neutral hydrogen is going to be progressively ionized by the stellar EUV flux. So obviously we need neutral hydrogen to get a Lyman-alpha transit. So if we completely ionize this tail, we're not going to see it. So there's two competing processes, right? Higher EUV flux drives more powerful outflows, but higher EUV flux also ionizes this neutral hydrogen tail faster. So the question is, which one wins? So let's think about our neutral hydrogen. Let's blast it with some EUV photons and ionize it. And now we have a partially ionized gas. Now let's fire a few more EUV photons in. Because the neutral hydrogen fraction has dropped, we're going to absorb less ionizing photons, and let's say we'll only ionize half the hydrogen atom, neutral hydrogen remaining now, and we'll let some EUV photons go through. So this is sort of obvious, but the photoionization rate depends on the neutral density. If you have a higher neutral density, you have a higher photoionization rate. So if you write that mathematically, the rate of change of the neutral fraction depends on the neutral fraction and the photoionization rate. So this is just an exponential decay, or if I solve that in log linear space, it's just a straight line. So now if I double the EUV flux, so I get 3 times, I get twice the mass loss rate, I start off with a higher neutral density, but I also ionize it much, much faster. If I do the opposite, I reduce the UV flux, I start off with less mass loss rate, but I also ionize it much slower. So if I'm optically thin to Lyman-alpha at some much lower neutral hydrogen density, it's actually the planet that's receiving the lowest irradiation levels that's going to give us the longest and deepest ionizing transits, because the tail is able to stay neutral much longer. So Lyman-alpha transit's fundamental observable is not how much neutral hydrogen you're throwing off to start with, but how long you can stay ionized, or the distance or time you spend before a typical neutral atom gets photoionized. So what you can do from these Lyman-alpha transits is take a Lyman-alpha transit, you can measure the transit duration, you can use the geometry you know of the planetary system to measure the neutral hydrogen tail length, and then you can use speed equals distance over time to find the typical launch velocity from the planet. And this is the key observable that we think Lyman-alpha transits are giving us, and this is the key thing we can test from our models. But there's also this key thing that you need to accelerate the gas before you ionize it, right? So you can get a detectable transit if the stellar wind or stellar radiation pressure can accelerate the gas radially towards the observer before you photoionize it. But if you photoionize it before you can stay neutral, then you're not going to see anything. And that's actually the answer to what's going on in this case that I said before. GJ436, low ionization flux, you can stay neutral many, many distances from the planet and see a whopping Lyman-alpha transit. But for this more highly irradiated case, it's ionized way too quick, even though it may be using mass. So this brings me on to the UV scope mission. And one of the goals of the UV scope mission is to do Lyman-alpha transits and statistically test our mass loss model. So you're going to hear a lot more from this mission, about this mission from Mark and others in talks later today. So I'm just going to highlight on what we'd like to do with the Lyman-alpha, which is to do Lyman-alpha transits for a large ensemble of planets, measure the velocity at which gas is being thrown off the planet, and with a sample of about 50 Lyman-alpha transits, we should be able to distinguish various mass loss models, such as the photoevaporation model or the core pad mass loss model. So thanks very much. I'll leave it there and I'll take questions, and we're going to hear a lot more about this stuff in the next few talks, and take a look at the posters as well.
Awesome. Thank you, James. Looks like we've got a number of questions. I think first up is Ofer Cohen.
Hey, James, very nice review. What velocities do you think the outflow can be accelerated to in these cases?
So it depends on the driving mechanism. So if it's pure photoevaporation, so pure thermal heating from EUV and X-ray photons, then you can heat yourself up to something like 10 to the 4 Kelvin, and then the sort of maximum temperature velocities you can reach are a few times the sound speed of that gas. So something like 20 to 30 kilometers per second, absolute maximum. If you're going to talk about something like core pad mass loss, which Akash is going to talk about a bit later, where it's thermally driven from the heating of the core, then you're going to get much slower wind, something like 2 to 3 kilometers per second. And if you can use any kind of magnetic acceleration mechanisms to help you get out the planet's potential, then you can reach even higher velocities, something like 50, 60 kilometers per second. So by using Lyman-alpha transits, hopefully we can measure this velocity and actually work out which one is the dominant process.
Next on the list is Zafar.
Hey, James, great talk. I was wondering if there are any other hydrogen lines that have been observed in transit and if they're information rich. Thanks.
Yeah, so one of the other ones that you would be wonderful to get is H-alpha. But H-alpha is very variable on the stars. There have been a few claims of H-alpha detection, and they've been sort of refuted back and forth. So I think one of the things with these UV transits, specifically for atmospheric escape, is because the star can be so variable, we're going to want to go back many, many times. And another good one is the helium-10 830 angstrom line that you're going to hear from Antonio later today. But if we could get Lyman-alpha and H-alpha, then you get a much better probe of what the ionization fraction of the gas is, and then you can say something more quantitative about the output.
All right, great. I think we're just about out of time. So in order to stay on track, I would encourage the other questions. Looks like there's 3 more questions to maybe throw those in the chat and maybe James can answer them there. So thanks a lot, James. Next up, we've got James Rogers also from Imperial College London, telling us about unveiling the birth population, the planet population at birth. All right, take it away, James.
Hi, hopefully everyone can hear me okay.
Yeah, sounds good.
Okay, so hi everyone, I'm James Rogers. I'm also from Imperial College London. James is my supervisor and he's given a fantastic introduction to photoevaporation. And today I'm going to talk to you about a paper that we released recently that is talking about how we can use photoevaporation to unveil the planet population at birth. And so here I'm showing some demographic data. This is from the California Kepler survey. And in the orbital period planet size plane, we see this fantastic substructure of the population of super-Earths and sub-Neptunes that are separated by the radius gap. And the question is, if we take the assumption that photoevaporation is the mechanism that is driving this evolution and this substructure, what can we learn? And so another way of saying this is, if we were to rewind the photoevaporation clock, what constraints can we place on the population of planets that we're looking at? And in fact, by doing so, we get constraints on 3 really important distributions: the core mass distribution, the initial atmospheric mass fraction distribution, and the mean core density distribution. And it goes without saying that these 3 distributions are going to be really important to place constraints on planet formation models. Any constraints we can place on these will be immensely helpful. And secondly, these distributions are not easily observed by standard survey techniques. So I've been quite vague so far about what I've actually been doing. So let me now lay out the way that we've been able to do this inference. So first we set up 3 arbitrary distributions for these distributions of interest. For now, it doesn't matter what they look like, but we draw a random ensemble of planets from these distributions. So we have our core masses coming from here, our initial atmospheric mass fractions coming from here, and our core densities coming from here. Again, it doesn't matter what these distributions look like for now. We then evolve those planets through UV and X-ray photoevaporation. So we form the radius gap, we form super-Earths, and we also form sub-Neptunes. We take those evolved planets and we observe them with a synthetic Kepler light transit survey. So this models the bias and the uncertainties, and we create synthetic data, which is then compared to the real CKS dataset. And you can see right now I've got a pretty bad fit, but eventually what you do is you construct a likelihood function, and this all comes together in a hierarchical inference problem. So what you're learning here is, what do these 3 distributions have to look like in order to fit the data that we observe from Kepler? So just a quick recap, these are the 3 distributions that we get from assuming that photoevaporation is the leading driver in the evolution of closer next planets. So let's go and have a look, see what we inferred. So to begin with the core composition distribution, on the left, I'm showing the posterior that we infer to fit the Kepler data. So on the x-axis, I've got the composition, which ranges from 100% ice to 100% silicate to 100% iron in these cores, with fractions of these three substances in between. And what we infer is that these cores have to be iron rich in order to fit the data. And if I plot Earth composition, which has an iron mass fraction of around 33%, we see that we're consistent with an Earth-like composition. On the right-hand side, I'm showing the standard deviation in this distribution. So how much can the composition vary while still fitting the data? And whilst we can only fit an upper limit, what we see is that the width of this distribution has to be very narrow to still fit the data. And it's interesting to have a look at the implications of this. If we look at planet formation models, so very broadly speaking, there are 2 ways to form a core. You can either form a core interior to the snowline from the silicates that are present in the protoplanetary disk, or you can form your core outside the snowline where there's an enhanced mass fraction due to ices. And then this core can migrate inwards where we might observe a super Earth today. And the predictions of these two scenarios, again, very broadly speaking, is that you're either going to end up with a rocky core or an icy core. And yet we've inferred that these cores have to be rocky in nature in order to fit the data. So already some interesting implications coming up. So now looking to those other distributions, and for these next two, we actually allowed them to be completely arbitrary using generalized polynomials. So they really could have ended up looking anything like anything they wanted to do. But what we find is that the core mass distribution is peaked. We find a peak at around 4 Earth masses. And we see a steep decline in occurrence for cores beyond 20 Earth masses, which makes sense because these are the cores that are going to go on to accrete large self-gravitating atmospheres and become Jovian planets. Similarly, the initial atmospheric mass fraction distribution is also completely arbitrary. It could be anything it wanted to be, but we find it's also peaked. And we see this peak at a couple of %, which is what James was showing just before. These are the sub-Neptunes, and this is essentially the distribution of atmospheres before photoevaporation happened. If I then evolve that distribution, we see the same peak. These are the sub-Neptunes that we observe today with a couple of % hydrogen-helium atmospheric mass. And then we also see this large spike at 10 to the minus 4. And this corresponds to the planets that have been stripped of their primordial hydrogen-helium atmosphere and have become super-Earths. Thank you. What's interesting is that if you look at the population of planets that were born terrestrial, so those that were born with a negligible atmospheric mass fraction, and compare that to those that were completely stripped through photoevaporation, you see that the latter actually dominates. And so what this is suggesting is that if we observe a planet today that is terrestrial in nature, it is much more likely that it was that this happened through evolution and not through formation. And finally, a question I get a lot is, what about core pad mass loss? And so we're going to hear from Akash later, but to answer this question, we've actually very recently written a paper about it. And so this will be coming on the archive in the next couple of days. And so I've been working with Akash, James, and Hilke, and we're introducing a new way of doing model comparisons between the two, because it's true that you could have done this entire analysis with core pad mass loss, but we want to know which model is actually, if it is one, which one is leading or dominating the atmospheric evolution. So we're proposing a new way of doing model comparison, and we do similar transits, synthetic transit surveys to investigate how many planets we might need to observe to do this on a demographic level. So I will leave you my conclusions, and happy to take questions on any of the model comparison stuff or anything else that I've spoken about today. So yeah, thank you very much.
Great, thank you, James. We've got a question. First one up is Laura Flagg.
Hi. When you say that photoevaporation is the dominant cause, what do you mean by dominant? Is it 90% of the mass loss, over 50, just approximately? What do you mean by that?
So in the model that I'm using in here, I'm assuming that 100% of the mass loss is due to photoevaporation, but you could do this process by you could do it with 100% core pad mass loss model. So essentially we're looking at different models of mass loss, and eventually if you have a combined model, you might be able to do this inference problem with a combined model of photoevaporation and core pad mass loss. But the assumption is that in this inference, we've assumed 100% photoevaporation.
Thanks.
Next question from Leah.
Yeah, I was just wondering if you could expand a little bit upon what XUV luminosity models you used and whether it changed over time and how long you evolved the systems. Did you assume they all evolved for the same amount of time?
Sure, yeah. So we assume all the planets evolve for the same amount of time, which is 3 billion years in this model. So the majority of mass loss, according to the model that we're using, is that we're looking at the XUV flux, which is saturated up to 100 million years, and then very quickly decays after that. So you're going to get most of the mass loss occurring in the first 100 million years. I should say, though, this new paper that's coming out in the next couple of days, we look at a slightly more sophisticated way of looking at the XUV flux, with how this varies with host stellar mass, But in terms of this inference work that we've done, we assume that all the mass loss, or the majority of the mass loss, is happening in the first 100 million years due to the XUV flux.
Thanks.
All right, let's do one more question from Ward.
Hi, great talk. That was absolutely fascinating. My question is about the inference framework. I was wondering in the negative log likelihoods how false minima are approached or handled by the inference framework.
False minima are, so essentially we're doing a big Monte Carlo Markov chain. I can quickly, I do think I have a backup slide somewhere of just looking at the likelihood. Essentially, you're looking at two contributors to the likelihood. You're trying to match the number of observed planets and then also trying to match the shape of this distribution. So you're trying to match the observed planets, which I'm plotting in black, with the contours, which is what the model is predicting. We don't actually find too many local minima when we explore parameter space, I think, is maybe the best answer. Like for the density, for example, the core density, there's only one specific density that puts the radius gap in the correct location that matches the data. So in terms of those kind of parameters, you don't really see too many local minima. I'm not sure if I have a better answer than that right now, but happy to chat offline if needed.
Thanks, this is fascinating.
All right, thanks, James. I think we'll have to move to the next talk, but if there are any other questions for James, feel free to throw them in the chat. Next up, we've got Leonardo dos Santos, who will tell us about the atmospheric escape in Neptune-sized and smaller exoplanets from University of Geneva, by the way.
All right, hopefully you can hear me and you can also see my screen.
We see your desktop background.
Yeah, I'm about to play it there. There you go. Now I should be able to see those slides. All right.
Yep. Looks and sounds great.
Cool. So thank you for having me. I'm gonna give more of an observational side of atmospheric escape, which is the main thing that I do in my research. And I'm gonna focus on subneptunes and super Earths. The reason being is because they sit at this interesting position in the mass versus radius diagram, where they exist in a parameter space that is riddled with modeling degeneracies. So for instance, if you look here in this diagram, and come on, there you go. So this gray region here on the left, bottom left, is the terrestrial worlds, and the one here on the top right is gas giants. What we have here right in the middle is the subneptunes and super Earths. As you can see, they are at this region with a lot of degeneracies. So in other words, they can be made of many different mixture combinations of rocks, ices, and gas, and still fit the observed masses and radii. And we think one of the keys to solve this puzzle lies in understanding their atmospheric escape history and evolution. So hence the motivation to observe atmospheric escape. So this is just another way to look at them that is a bit different from the starting motivation that James Owen showed in the beginning. But it all comes down to the distribution of detected exoplanets that we have so far. So this is the good old bolometric radiation versus planetary radius. And we see two striking features in it that we think are caused by atmospheric escape. They are the hot Neptune desert and the radius valley, which has been mentioned. So I'm not gonna discuss hot Neptune desert that much here because it involves Neptunes, and I'm going lower than that. But yeah, both of them we think are caused by atmospheric escape, and how that happens at the time scales of their evolution and imprints features at the demographic level. All right, so since both James have already talked at length about the radius valley, I'm gonna skip what I was gonna say, so I have more time for other stuff. So there are many hypotheses to explain these demographics, and the first is photoevaporation. We also have core power mass loss. Migration history, it seems to be more important for the formation on the hot Neptune desert, maybe not as much for the Radius Valley, but anyway, I just listed here for completeness. And more recently, there is also a proposal that primordial formation features could cause the Radius Valley as well, which was recently proposed by Lee and Connors. Or it could be just a combination of all of that. But I'll leave that to the modelers to decide, but using our observations. So classically, the Lyman-alpha transit spectroscopy in ultraviolet has been the workhorse of atmospheric escape. This is the first detection of Lyman-alpha transit at the hot Jupiter HD 20945AB, good old HD 209. Here on the left, you have both the in-transit and out-of-transit Lyman-alpha profiles, and here on the right, you have the light curve of the Lyman-alpha bandpass. And we see this decrease of approximately 15% in the stellar light, while the opaque disk of the planet is only about 1%. So all this additional absorption is caused by the exosphere of the planet. Fast forward a few years, and we have also discovered that Neptunes, they seem to be at this sweet spot where they produce very deep Lyman-alpha features. So for instance, and that happens because they have plenty of hydrogen and helium to shed, and they also have lower gravity than hot Jupiter. So this is why they lose their atmospheres like there's no tomorrow. So the two Neptunes for which we have found large extended exospheres are GJ426b and GJ347b. This second case here is very interesting because we also see absorption in the red wing, but I don't have time to discuss about it, but please ask questions to other people, not to me, about the absorption in the red wing. Now there are many, but going to the sub-Neptune and super-Earth planets, there are many challenges to detect and interpret atmospheric escape in them. First one is that if you detect hydrogen or in Lyman-alpha, the interpretation can be a bit ambiguous because the escaping hydrogen could either come from a primordial atmosphere reaching hydrogen and helium, or it could come from an atmosphere reaching water, and the water can photodissociate and produce hydrogen to escape. Now, the escape of helium, which is done in infrared, it's not necessarily ambiguous. So if you detect helium in it, you can securely say that you have detected a primordial atmosphere, but the detection depends on a very fine tuning of the host star. So it's a bit more limited than that. There's also the escape of metals in the ultraviolet. It seems to be only observable or feasible for a very bright host, and I'll briefly mention it at the end of the talk. Just going to helium a little bit. I know this is an ultraviolet conference, but helium is an infrared. But helium is also important. I think one of the most important results that we have found so far for some Neptunes and escape was published by Casper last year and collaborators, in which they used the CAC near-spec spectrograph to look for helium in 3 sub-Neptunes and super-Earths, which I highlight here in red, and all of them were non-detection, so we have only upper limits. And more recently, there's also the non-detection for 55 concrete. So far, only non-detections for them. Lyman-alpha seems to be a bit more promising. We have a tentative detection for Lyman-alpha transit for the sub-Neptune K218b, but we deemed that as tentative because we had only 1 transit and not enough baseline, out-of-transit baseline. So this experiment still needs to be reproduced to be confirmed. And finally, another important result that came out recently is the detection of ionized carbon escaping the super-Earth Lyman C detected with HSC and the COS spectrograph. Now, and the authors, they conclude that this planet has a thick atmosphere abundant in heavy volatiles. Ideally, we want to do this for other super-Earths as well, but we need a very bright host star to observe transit that is only 2% deep, as you can see, only 2%. Just so you have an idea, for GJ426, the precision that we got by accumulating several transits was about 10% in the precision for the carbon flux. So we can do this only for very bright hosts. All right, with that, I think I'm running out of time, so I'll leave you with the take-home messages, and I'm open to any questions that you may have. Thank you.
Awesome, thanks, Leo. We got time for one or two quick questions, if there are any. One I can go ahead and ask is, I'm kind of curious how many good targets there are for these types of observations. Are we target limited in any way, or are we time allocation committee limited?
I think for Lyman-alpha, there are many new exciting targets being discovered by tests. And I mentioned this in one of the previous breakout sessions. There's a lot of very nice planets being discovered by tests, specifically because they are being found in host stars that are within 50 parsec or so. And these are amenable to Lyman-alpha transit spectroscopy. So these are definitely good targets. So it's not like we're running out of them. We're actually piling them up. And it's been difficult to get observation time of HSC to observe them. Now for helium, I think there is sort of an untapped potential for helium in the southern hemisphere, because all of the detections done so far were in the northern hemisphere, because this is where all the telescopes are located that can do helium spectroscopy. And in the southern hemisphere, in the near future, we're going to have CryoS Plus and also NUPES that can do helium spectroscopy in there. So I think there's going to be this new batch of helium detections on southern planets as well. And now for metals, as I said, we need very bright hosts like Lyman-C to get a detection, unless we have a lot of metal escaping. So yeah.
Awesome. Well, I think we'll have to move on to the next talk, but there's one other hand raised, so maybe we can answer that in the chat. So next up, thank you, Leo. Next up, we have another invited talk from Ruth Marie Clay from the University of California at Santa Cruz, who will tell us all about strategies for directly probing hydrodynamic escapes. Take it away, Ruth.
Thank you. I'm really enjoying the conference. Yeah, so I'm going to be talking about strategies for directly probing hydrodynamic escape. Since this conference is a broad audience, I thought I'd give a little bit of an overview of some of the topics that many of the other people speaking are talking about in more detail. And then also at the end, I'm going to present a signature that I think is fun and I think that we should be looking for. Okay, so I'm going to start with direct and hydrodynamic. So why do we need direct probes of hydrodynamic escape? As we've seen, we know planetary atmospheres are escaping in the solar system. We see these features in I call this the evaporation valley, but I should really call it the period valley, because as Leonardo said, there are several possible explanations for this valley in the super Earth population. And also the hot Neptune desert, as Leonardo also brought up, has been interpreted as a signature of atmospheric escape. So these are very strong escape features, if indeed that's what they're coming from. We're talking about losing a huge amount of mass from planetary atmospheres compared to escape that's seen in the solar system. But for these really extreme mass loss processes, we don't really have any direct observational validation that the models that we're using to describe the escape that's producing them is actually correct. So let me just give some terminology. At least this is how I use these terms. I know some people use them differently. So there are two classes of escape mechanisms, and each of which can be thermal or non-thermal. There's kinetic escape, that's loss to space of individual atoms, and hydrodynamic escape. So that's bulk outflow of a collisional fluid. And these can be both thermal or non-thermal. So the limits of thermal escape in the kinetic regime are Jean's escape. In the hydrodynamic regime is what I'm calling hydrodynamic escape. So these are all thermally driven outflows. So they're driven by the temperature of the gas. But of course, kinetic processes, as we heard all about yesterday, dominate loss from most solar system planets, and they're typically not dominated by the thermal escape, but rather by charge exchange, sputtering, other magnetic field mediated kinetic processes. And I'll just point out that you can also have hydrodynamic escape that is not thermal. You could have Roche lobe overflow. We've seen that in at least one system. In principle, you could have ram pressure stripping if you have a really strong stellar wind. You could have collisional erosion that could be important for smaller planets where you just collide the planets together and throw off their atmospheres. Okay, so I'm going to be talking about thermal hydrodynamic escape. All right, so why do you have this? Thermal hydrodynamic escape is classically described as a Parker wind, and in these planets, it's actually more of a classical Parker wind than the solar wind, which is magnetically mediated. And the basic idea is if you try to put an isothermal atmosphere in hydrostatic equilibrium out to infinity, it doesn't work because you have pressure at infinity, bad, and so it accelerates the gas outward. And the energy for the PDV work that's done in this very simple case comes from the isothermal assumption, but in actual reality has to come from somewhere, right? And so there are a couple of places that have been proposed for where that energy comes from, which are photoevaporation and core-powered mass loss, which I'll get back to in a sec. All right, so how do you tell if thermal escape is genes or hydrodynamic? We heard about this yesterday. You can check whether the gravitational binding energy versus the thermal energy at the exobase, which one of those wins. So the exobase is where your atmosphere becomes non-collisional. So when you're looking at a planet where you have a lot of information, this is a very sensible way of thinking about it because you know where your atmosphere becomes non-collisional, you know how hot it is, and you can compare the gravitational binding energy to the thermal energy at that base. When we're looking at exoplanets, it's a little harder to think about it this way because the temperature and the exobase location depend on your outflow structure. So another way of saying the gravitational binding energy versus the thermal energy at the exobase is whether your Parker wind, your outflow, accelerates to supersonic velocities while it's still collisional. That's because Parker winds, they become supersonic, and at the sonic point critical location where that happens, the thermal energy is comparable to the gravitational binding energy. So if you're still collisional, once you've thrown out your outflow and now you're moving at supersonic velocities, then you are in a hydrodynamic wind and you don't care what happens after there. So those are basically the same thing, but they're thinking about it from a little bit of a different direction. And again, the key thing here is that because the temperature and escape rate are coupled by the cooling from PDV work in the outflow, and the exobase location depends on your density, so like where your energy is deposited, how much mass is flowing out, you need to understand the dominant heating and cooling mechanisms in your model to really understand what regime you're in and what kind of outflow you have. All right, so as I said, and people have said, thermal escape can be driven by the heat of formation stored in a planet's core. That's core-powered mass loss. I'm going to be talking about photoionization, photoevaporation driven mass loss, which as we've already seen, you bring in an XUV photon that photoionizes, for example, a hydrogen atom. You kick off an electron, it collides with its neighbors, it shares that extra energy from the ionization, it becomes thermal energy, and then it's heating. And then it's just that heat that generates a pressure gradient that blows off your wind. Okay, so how does this compare to what's going on in Earth's thermosphere? Our thermosphere also is heated by photoionization by those same EUV photons, ionizing photons, but we do not have hydrodynamic escape going on from our thermosphere, thankfully. And what happens to that energy is instead of blowing off an atmosphere, it is conducted lower in the atmosphere to the mesopause, where the atmosphere is dense enough to radiate away that absorbed energy in carbon dioxide 15 micron emission. So what happens to your thermosphere is sort of a follow the energy kind of problem, right? Here's another example of thermospheric energy balance on Venus and on HD 209. On Venus, your energy is coming in as EUV heating up in the top part of the atmosphere. It's leaving as conduction down to lower atmosphere in the atmosphere, where it's then radiated away in 15 micron emission. Whereas in HD 209, you cannot conduct because there's just so much energy coming in so fast that it can't be conducted lower, and it just ends up driving escape outward. So all of the cooling there is done by PDV work. So in other words, if your thermosphere can find a way to radiate away all of that energy that it's getting from photoionization, you won't drive a big outflow. And if it can't, you will. So here's just a cartoon of that. You absorb your UV and you either radiate it away or you get a collisional fluid outflow. All right, so hopefully I've convinced you that we actually need to know something to do this modeling. And I think that, the many of us here who've done this have, do know something, but as a theorist who has some, what's the word, humility, right? I think it's always good to actually have observational validation that what you're modeling is what's actually going on. Okay, so what about observed mass loss rates? Well, they are model dependent. So we've talked about the Lyman-alpha absorption line. It is obscured at line center. In these models, if you could look at Lyman-alpha in line center, it would be basically obscuring the whole star for most of these systems. But the outflow velocities, as James said, are only expected to be a couple of tens of kilometers per second. So if you look at the gray region of that line, the whole main part of the outflow is obscured. And we're only looking at what's happening out in the line wings where we need additional physics to understand what's going on. So we're not directly measuring the velocity of the outflow. And the second thing is if you're looking at something like Lyman-alpha, you're looking at neutral hydrogens. You need to know what fraction of your gas is ionized. So this is just an example for low on the left and high ionization EUV fluxes. For the same planet. And you can see that you can have an outflow that's actually mostly neutral and one that's almost entirely ionized, depending on your EUV and at young ages XUV environment. So when we measure absorption in Lyman-alpha, we're not getting a direct measure of the velocity, and we're getting a direct measure of the neutral hydrogen, but not all of the hydrogen. So it's model dependent. Okay, that's good, but it's model dependent. That's what I just said. Okay. And just a quick comment, right? Of course, we do have some terrestrial or solar system evidence for hydrodynamic escape in residual isotope ratios, but that also doesn't give a direct probe of mass loss rates. Okay, so what are the ways to get direct probes? We've heard about a few. There are the optical and infrared lines that have been measured recently in H-alpha and helium-1080 that are so exciting. There are metal lines, which are just starting to come into their own. I actually hadn't heard about that Garcia Munoz result. I'm so excited about it. And then there's Lyman-alpha, which I've said is tricky, but I think that if we take a population level approach, as James Owen described earlier, can be very useful. All right, so optical and infrared lines, H-alpha and 1080, they've been observed. Those are just examples. The key thing to understand about these lines is that you are in these outflows, it is too cold to thermally excite atoms into the hydrogen N equals 2 state in the case of H-alpha, the metastable state appropriate for helium-1080 in the case of helium. And so in order to populate those levels, you have to have electrons going through a recombination cascade. And that recombination cascade has to be understood in the context of the expanding wind in order to understand the populations in those levels. So that's something that you can do, but you need a really good understanding of the incoming UV flux from the star. I think we're going to hear more about this from Antonia in the case of helium. So you need to have confidence that you can understand this level population in the context, again, of the outflow and its implications for recombination, because if you're outflowing fast enough, you don't actually recombine at all. Okay, so these lines are generally, they generally require densities that are within a couple of planetary radii. Oh, and I should have said that that H-alpha and helium-1080 tend to be available for different stellar EUV environments. So the higher UV, you're more likely to see H-alpha, and for the helium, more moderate levels are required. And that's again, because you need to get the appropriate population levels in these recombination cascades. All right, metal lines. Metal lines is something that I'm really excited about, but as we've also heard, have not really come into their own yet, because we haven't had the sensitivity or the ability to stack enough transits to see these. if metals are lifted to the base of the outflow, they will be carried away by drag, but there isn't a guarantee actually that metals will be lifted by turbulence in the planet's atmosphere up to the top of the atmosphere, where these outflows leave from. But UV transitions of metals, if they're there, in particular, oxygen 1 and carbon 2, because of their oxygen 1, because it has a similar ionization potential to hydrogen. Carbon 2, it's because carbon 1 is just very easily ionized. So carbon 2 is the one where you're going to sit there with a similar ionization potential. Should be observable, and we just heard that carbon 2 has now been observed. Okay.
2 minutes.
Thank you. All right. So why is Lyman-alpha absorption only sometimes seen? As James argued, if you are pushing, you need to push your outflow into the observable window. So this is a 3D hydrodynamic simulation with photoionization included for a hot Jupiter in the presence of a weak, medium, and strong stellar wind. And what I want you to notice is that in these medium and strong wind environments, gas is actually pushed outward by the stellar wind to larger velocities toward the observer. And this can actually allow you to push outflowing gas into the velocity range that is detectable with Lyman-alpha transit measurements. And for lower mass planets, we've gone ahead and done a calculation showing can you actually be pushed into that observable range before you're ionized by your ionizing photons. And James has shown that you can actually get a great relationship between whether you expect to see a transit and whether you do see a transit. So you need to accelerate that gas into the blue wing. There are other things that could be shaping the outflow. So the point here isn't necessarily that the stellar wind is the only possibility, but that we need to test it. So here I want to show you some examples of what this looks like, and this is what I'm going to end with, but it's going to be a couple slides. If you look in the middle, you can see that in the leading arm of this outflow, you have gas accelerated toward the observer. So these are some absorption calculations through these simulations at different velocity bins or different wavelengths relative to the observer. And you'll notice that at -50 kilometers per second, that's the moving towards us, the blue shifted end, you can see a big feature ahead of the planet because it was pushed ahead. If you look at this in different phases, so now here the green is mid-transit and the yellow is before the transit, you can see that there's a lot of the absorption is in the blue wing where it could be observed. So the blue line here, just region, is where you could observe it. And this is really fun. So now if you look at the time on top in hours from transit center, and just look at the blue curve on here, that's the blue wing absorption. You see that in the middle of the transit, you don't get much excess absorption in the blue wing over just the planet's absorption. But if you look 6 hours earlier, you'd see a ton more. And people don't usually look 6 hours earlier. Isn't that fun? We should look 6 hours earlier. Okay, what about if the strong stellar wind? Let's look at this one. Okay, here's these same things, but for the strong stellar wind, you can see the absorption plots on the bottom. Look at the top left. Time from transit, the blue line. In transit center, you see a little bit of excess, but if you look 6 or 8 hours later, then you should see a ton. We don't usually look 6 or 8 hours later. So we should look for this. And I just want to point out that this is for hot Jupiters. The reason that we can see this so late, even after the gas has been ionized, unlike for the hot Neptunes that James was talking about, is that for hot Jupiters, you have so much gas flowing out that even in ionization equilibrium later on, if that tail gets pushed into our appropriate velocity bin, you have enough gas there to see absorption. All right, so I'm going to skip this. We have some other planets going on, and I'll end here with a summary of the different features. And I just want to highlight that observable Lyman-alpha from gas and ionization balance at large distances for hot Jupiters would be a really fun thing to look for. And that to really test these things, I think that we need population level model validation from a mission like UV-scope that can look at a wide range of planets and see their variable signatures, because none of these features can give us all of the information that we need in one shot. All right, thanks.
Awesome. Thank you, Ruth. That was great. It's really exciting. We got time for maybe a couple quick questions. First up again is Ofer.
Hey, Ruth, very nice talk. Very cool simulations. How do you think a strong planetary field will impact the interaction of the stellar wind on the outflow?
Sorry, how do I think a strong what?
A strong planetary magnetic field will affect the interaction of the outflow and the wind.
Yeah, so for so a strong magnetic field can absolutely affect the outflow. So it depends on how strong it is. If the field is, if we're talking about a young star that has an incredibly strong field, it could direct the outflow not in these tails at all, but on field lines that are toward the star. If the planetary field is strong as well. If you're looking at a moderately strong magnetic field, then you could direct your outflow toward the poles. But then once it gets outside of the Hill radius, then you could end up having a similar sort of feature. So it depends. But yes, it could be very important, particularly for hot Jupiters.
All right, we got a comment in the chat from Cynthia Froning that they saw evidence of early transit ingress in the NUV versus optical in WASP 12b, which is interesting. And we got time for probably one more quick question from Leo Dos Santos.
Hi, Ruth. I find it very intriguing, the early ingress or the delayed egress that you inferred from your models. I think that's very exciting. How sensitive is that delayed or early feature? How sensitive is it to assumptions that you make about the system?
It is, so fundamentally, the amount of absorption that you're getting is coming from the density of the gas in ionization balance with the star, which again, for sub-Neptunes or super Earths, in that ionization balance, it's not going to be detectable. But for Jupiters, you can have a high enough density. That density, I don't think, is hugely dependent on assumptions modulo the magnetic field situation, because it's essentially coming from, the Hill radius or a few Hill radii from the star, sort of pulled back by the Keplerian motion around the star. So it depends on and then the other thing that it depends on is this, like when that will happen depends on the stellar wind strength, because you have to push the gas until you have to have enough momentum injected into that tail to push it into the velocity range that we can see. And for the sub-Neptunes, like for GJ436, you can push it much more quickly. That's why we can see it right away in this model. You don't have to wait, because there's just less total mass that you have to push with the wind. So it depends on some assumptions, but I don't think that they're, I guess I would turn it around to say, I think that the assumptions are generic enough that this is a useful test. If we don't see this, then this is not the right framework for thinking about what's happening. Yeah.
Thank you.
All right, great. Thanks, Ruth. We'll have to move on to our next talk. So Antonio, if you want to put your question in the chat, that'd be great.
Yeah, and I got a friendly correction that I should be saying 1083, not 1080. So thank you for that correction, and everybody else don't listen to me.
Oh, it's 10:8:30. We'll have to do a vote.
Sorry, 10:8. Okay, all right.
That's in angstroms, but if you're talking nanometers, you're A-okay, Ruth.
All right.
All right, great. Depends on significant digits. Let's see. Okay, next talk, we have Akash Gupta from UCLA, who will tell us about understanding the radius valley as a byproduct of planet formation, the core-powered mass laws.
Thank you, Josh.
Yeah.
Hi, everyone. I'm Akash Gupta. I'm a PhD candidate at UCLA, where I work with Thermospheric. And so in this talk, I would like to discuss how we can understand the radius valley as a byproduct of planet formation process itself. Now, thanks to the speakers so far, oops, sorry, just a second. Yeah, so thanks to the speakers so far, I don't think I need to give an introduction to the radius valley. And so let's just jump directly into the main question at hand, which is why does the radius valley exist? And as people have already alluded to, there are multiple mechanisms that have been proposed to explain the radius valley, but only a few of them can explain a multitude of the related observations. And so in this talk, I would like to focus on the core part mass loss, which is one of the ones that can explain a multitude of observations. And so let us first understand what is the idea behind this mechanism. Now, the story of planet formation starts with a gas cloud collapsing under its own gravity and leading to the formation of a star and an optically thick gas disk around it. Now, as the star, like in this disk, as things cool down, particles start to form and they start colliding with each other and grow with time. And you basically get the process of core accretion. Now, during this process, what is really happening is that as things are coming together, the gravitational binding energy is getting converted into heat energy. Now, all this heat energy can get radiated away very quickly if this process was to happen in empty space. But if there is an optically thick gas disk around, it's not going to be that easy. More importantly, if there is a gas disk around, the planet should also be able to accrete a hydrogen-helium envelope. And once this envelope becomes optically thick, any energy loss from the planet will be regulated by the radiative convective boundary, the thermal diffusion, the radiative convective boundary. So basically, this optically thick atmosphere will start to act as a thermal blanket because the cooling timescale will become much longer, allowing the planet to hold on to its primordial energy from formation for a much longer time. And it is this internal energy and the bolometric luminosity that can drive atmospheric mass loss at a later point of time via a Parker-type hydrodynamic outflow. And so if you follow a planet's evolution on this pathway, a planet can either become a super Earth or a sub-Neptune, depending on if it holds on to its atmosphere or not. But what is it that dictates, which of these two cases happen? Well, there are a number of considerations that influence this, but the most important one is the balance between the cooling and the mass loss timescale. So what I mean here is that, well, let us say there's a planet for which the cooling dominates or the cooling timescale is shorter than the mass loss timescale. For such a planet, the atmosphere will cool and contract much faster than it can lose mass. And so what will happen is the atmosphere all of a sudden will be much deeper in the gravitational well of the planet. And when that happens, it will become harder for the planet to lose its atmosphere. And as this goes on, it will soon become, any mass loss will soon completely cease and you will get a sub-Neptune. On the flip side, if the mass loss is what dominates or the mass loss timescale is shorter than the cooling timescale, the planet will end up losing most of its atmosphere and you will get a super Earth. Now this, along with the fact that a hydrogen-helium envelope to core mass fraction of even a few percent can almost double the size of a planet, can explain the radius valley and the sudden jump in planet sizes from the small super Earths to the large sub-Neptunes. So now that we have an idea of what's really the idea behind core part mass loss, let us talk about this question. How can we distinguish the driving causes of the exoplanet radius gap, which is one of the top 10 big questions at the symposium? And so let me give you a quick rundown as someone who has been working on core part mass loss as that's what I can say on this subject. So let us first look at the planet demographics. And on this part, let us first try to figure out that if we are looking at a planet population out there, what can we say about the properties of those planets? So now what you're seeing is how the relative occurrence of planets changes with planet size. The red is a model, the gray is observation. And on the right-hand side, you're seeing the same thing, but in a two-dimensional space of planet size and orbital period. Something, without going into the nitty-gritty, something you can clearly see is that there's a good agreement between our results and the observations. But an important question then is that what does this agreement really tell us? Why is the slope this particular value? Or why is the radius value located at this planet size, planet radii? These are important questions. And so let us first understand what is going on with the slope. So as I just told you that these sub-Neptunes are the planets which cool dominantly, for which cooling dominates, or the cooling timescale is shorter than the mass loss timescale. And the super Earths are those for which mass loss dominates, or the mass loss timescale is shorter than the cooling timescale. This tells us that it is this balance between these two timescales that can tell us, that dictates where a planet ends up, and so can tell us the slope of the valley.
2 minutes.
Now, if you like do substitute like planet size and orbital period in this equation and do some analytical manipulation, what you figure out is that the slope is minus 0.11, which is in very good agreement with observation. We can do a similar exercise and also figure out what the location of the valley or the relative occurrence of super and sub-Neptune stellar, for instance, the bulk composition or the planet mass distribution. But I'll refer to our 2019 paper for this. Another piece of the puzzle is how the stellar properties impact the planet evolution. So on this part, let us see this example. So again, here we are seeing how the relative occurrence of planets changes in the planet-sized stellar mass space. On the left-hand side, we have our results. On the right-hand side, we have observations. And as you can again clearly see, there's good agreement between the results and the observation. And again, we can take this forward and also talk about what other inferences. We can make like a number of other inferences also based on these results, based on these agreements, as in the previous case. And we can similarly do the same thing with how the planet size changes other stellar properties like metallicity or age. Now, something that James Rogers alluded to, well, as some of you might know that at least when it comes to comparing the core masses and photoevaporation results, there's some sort of degeneracy there. So a way to overcome that degeneracy is to look at radius value in the three-dimensional space of planet size, stellar mass, and insolation flux, because this helps us, for instance, and the thing that we're trying to exploit when we do this is that at a constant insolation flux, photoevaporation depends on stellar mass, but the core mass loss does not. So for more details, I would refer, please wait for our paper, which should be out on arXiv in a few days. So moving on from like population level analysis to like individual planets, let's see what we can say here. So something that we do in our latest paper is that using under a Bayesian framework, we try to figure out that given the planet properties and the host star properties, what can we say about the planet's atmosphere mass fraction, composition, and mass loss rate? Idea being that we want to figure out if there are planets that could be undergoing atmosphere escape today. So in this paper, what we do is that we present a non-exhaustive short list of planets that are likely at losing atmospheres today. A good example of like from this sample is the SD86226C, which was discovered last year by TESS. Now it's a good example because it has a bright host star and because it's losing atmosphere at a considerable rate. Now something that is kind of a signature of core mass loss is that it has it predicts relatively lower mass loss rate than photoevaporation. And if you want to know more about this planet and the other candidates, I will refer you to our 2021 paper. But there's more to the story, and as many of the speakers have already pointed out, if we really want to go from theory to observations, and this is something that we intend to work on in the coming months. Plus, there's more that can be done. Like a spin-off of, a byproduct of this study was also that we were able to figure out planets that could be harboring atmospheres abundant with high molecular weight species, low density interiors, or both. But again, because I'm running out of time, I would refer you to our paper for more details on this. And that is it from me. Thank you so much. And I'll be happy to answer any questions.
Hey, thank you, Akash. Do we have maybe one quick question? We're running a little low on time. If not, then I'll encourage any questions to go in chat. It looks like there's some healthy conversation going on there, so maybe we can continue that. Without further ado, yeah, let's move to our last talk of the session. Thank you, Akash. Ofer Cohen, who will talk about the space environment and atmospheric Joule heating of habitable zone exoplanet TOI 700D.
Can you hear me?
Yes, we can hear you and we can see your slides.
Okay. Thank you for having me. It's a great pleasure. It's a great meeting. I will talk about the space environment of TOI 700D. This work has been published last year in FG. So the planet was discovered in 2020, or it was published in 2020. It's essentially one of the first test habitable planets or habitable terrestrial planets that were found. You can see here where it was observed. And 3 planets were detected in the system, and TOI 700d is believed to orbit at the inner edge of the habitable zone for this planet. So we decided to investigate the space environment around this planet and get some insight about its ability to sustain the atmosphere with respect to the stellar wind conditions. We used the AWESOME model, which was developed by the University of Michigan. It's a non-ideal MHD model for the stellar corona and stellar wind, and it accounts for wind acceleration and coronal heating by alpha waves, and it also includes some thermodynamic aspects. The good thing about this model is that it is extensively validated against solar observations in the solar case. And we use this model already to simulate the space environment of Proxima Cn-b and TRAPPIST-1. And in the two cases, especially in the TRAPPIST-1 case, we found that the space environment conditions were very, very extreme. We need to, in order to do this simulation, we need magnetic input of the stellar magnetic field. But because we don't have it, we need to look for a proxy star. And we found that CU-BU has a very similar parameters, with the exception of the rotation rate. TOI 700 is has a much slower rotation comparing to CU-BU. Here you can see the magnetic map of CU-BU. So what we did, we assume a scaling relation between magnetic activity and rotation period, and we scale this magnetic field down using that relation. But in order to provide some additional constraint, we also look at the solar conditions of the magnetic field of the sun that is kind of similar to these conditions, and we scale the sun up using the same scaling law. So we have two different inputs that we looked at. One is a scale down CU-BU map, and one is a scale up solar map that has roughly the same structure of the magnetic field. And again, we use the scaling law from Vidotto et al. For that scaling. The way we constructed the simulation is we use AWESOME for the solar wind and the solar corona structure. This is one model that we use. And then we extract the conditions, the stellar wind conditions along the orbits of TOI 700d, and we use these extracted conditions to drive a model for the planetary magnetosphere and ionosphere. And these two models are run in a coupled manner, so they talk to each other through the space modeling framework. And you're more than welcome to look at that and all this cutting edge technology that we can run a number of models together. But these two models were run in a coupled manner. So we use these conditions to drive the magnetosphere condition. This model is coupled with the ionosphere model. For the planet, we look at three cases for the magnetic field because we don't know what it is. We look at 0.3 Gauss, which is an Earth-like field, 1 Gauss, and 4 Gauss, which is more like Jupiter field, is much stronger field. Here I show the extraction of the stellar wind conditions along the orbit of TOI 700d. Again, we had two cases. One is the scale down CU-BU data, and one is the scale up solar data. And the nice thing here, we show both of them. And the nice thing you can see is that the two solutions are actually quite similar if you think about magnitude of the stellar wind conditions. So it's nice. We had actually two independent inputs for the stellar magnetic field, and we're able to obtain roughly same scale or order of magnitude of the stellar wind parameters that you can see here. One thing to note is that the stellar wind around TOI 700d is always superalfvenic, so it makes it much or very similar to the case of the Earth, which the solar wind is essentially almost all the time is superalfvenic, with the exception of very special situations that I won't discuss here. And in order to drive the magnetosphere model, we essentially sampled two cases. One is about here when the density is lower, and one is here when the density is higher. These peaks are essentially the crossing of the planet through the large Helmut streamers of the stellar magnetic field. So we have a higher density in these regions. This is the fast wind, or the so-called fast wind regions where the density is lower. Here I just show the solutions for the three cases of planetary magnetic field. So column 1, 2, and 3 is the planetary magnetic field for the three cases. Here on the last column, I show two reference cases for the Earth, one for just ambient typical solar wind conditions, and one during coronal mass ejection conditions. And again, we have the two cases of the CBU data or driven data and the solar driven data cases. Here I just show the calculation of the Joule heating for the or the Joule heating as a function of the three magnetic field cases for the planets. And the main thing to take away from here is that the two red dots on both slides or on both plots represent the reference Earth case that we simulated. And the main takeaway is that the Joule heating on TOI 700D seems to be much lower or lower than the case of the Earth. And this is in contrast to the simulations we made for the TRAPPIST-1 planets that had an enormous Joule heating that was even comparable, or it was a fraction of the solar constant. It was larger than the UV input. So again, very, very large Joule heating in the TRAPPIST-1 system. But here it's obviously much more moderate, and it's even relatively weak. So that's the main takeaway from this slide. And the main takeaway from this whole talk is that here I show solar wind conditions as measured by the Helios and Ulysses spacecraft. This is a solar wind data. And you can see Mercury is roughly at this distance. Here it's the heliocentric distance of the spacecraft. Venus is located around here. This is Mars location. And the main takeaway from that is that it seems like TOI 700D has conditions that are roughly similar to the solar wind conditions of Mercury. Now, if we say in general, we can say that these conditions are extreme or not. We don't know. But what we do know is that Mercury has no atmosphere, essentially. Venus has a very thick atmosphere, and we know that Mars is losing a lot of its atmosphere, even though the solar wind conditions at Mars are much weaker than those of Mercury. So the main takeaway from this talk is essentially just to state that even if we get some idea about the stellar wind conditions, the evolution of the planetary atmosphere depends on so many other things that we really need to take one planet and investigate all the processes that may impact its atmospheric evolution. And we cannot just isolate one or two processes together. What we know from the solar system cases is that real nature is composed of many different processes that are coupled together. And perhaps we need to think about exoplanets in the same way. Obviously, we're much more limited in the data we have, but it's extremely important to look at the solar system cases that we have more data and look at these processes and how they work together, and maybe from there go to the exoplanet case. So I'll stop there. Thank you very much.
Awesome, thank you. We have time for maybe one quick question I'd like to include. Yeah, John, go ahead.
Thanks, Ofer. I want to ask, so what's the biggest determining factor that sets the Joule heating for a given planet?
It's actually, so it's the stellar wind power, let's call it. And it's in combination of the atmospheric conductances. And the atmospheric conductance depends on the atmosphere below it. So it's kind of an integrated parameter. And we're actually not sure how, for example, extreme UV flux will affect the conductances. So it's actually something we try to calculate more consistently now, so we can have a better idea about what the conductances in these planets are.
Great, awesome. Well, with that, I think that's the end of our session. We'll go before going to poster pops before our break. So thanks to all the speakers. That was a great session. Loved learning about atmospheric escape. So thanks, everyone.
Great session. Thank you, everyone. So we'll hand it over to, and thank you, Josh, for doing such an excellent job chairing. We'll hand it over to Melody Cow, who I think is here, and she is going to run through our last set of poster pops. And I will remind you that if you want to rewatch these videos and see the posters in person and talk to the poster presenters themselves in real time, that's all happening in Gather Town in the poster room.
The Lyman-alpha emission line at 1216 angstroms is the brightest emission line in the UV spectra of M-dwarf stars and most exoplanet host stars in general. Knowing a star's Lyman-alpha flux is really important for understanding stellar chromospheres and exoplanet photochemistry, but measuring Lyman-alpha is really challenging due to hydrogen gas in the interstellar medium. As part of a Hubble Space Telescope survey called FUMES of young and old M-dwarfs, we have reconstructed intrinsic Lyman-alpha profiles from low-resolution STIS spectra for the first time ever. We find that precise reconstructions, like those achievable with STIS's higher resolution gratings, are achievable for stars with intrinsically broad emission lines, like young M-dwarfs and earlier type stars. However, the vast majority of M-dwarfs have intrinsically narrow lines, and precise Lyman-alpha reconstructions are not generally achievable at low spectral resolution for these stars.
Hi there, my name is Gerard Van Bell, and I'd like to tell you about LightBeam, which is a mission concept we've been working on for the first long baseline optical interferometer in space. LightBeam achieves this by flying a small spacecraft that becomes a big spacecraft through the use of 3D printing in space. This technology has actually already been flying on the ISS for a number of years, and we propose to extend that to an observatory mission like this. We actually have NASA funding that has been going into demonstrating the in-space manufacture for this particular mission, as well as the optics payload already. The extreme resolution that you get from a 20-meter beam at the visible and near UV goes down to about 3 milliarcseconds. We'll use that to look at disk structures, such as the inner pixel of these ALMA YSOs, and you can also look at the cores of nearby AGNs. We're looking for science team members right now, so if you're interested, we'd be delighted to hear from you. Thank you very much.
Hello to everyone at Stars and Planets in the Ultraviolet 2021. I'm Girish Davuri, and my poster describes how we reconstruct the extreme ultraviolet spectra of cool dwarfs. We take X-ray and far ultraviolet observations, use a method called differential emission measure, and infer the unobserved extreme ultraviolet spectrum. The first paper in that list describes our method in detail. The other two apply it to TRAPPIST-1 and Barnard star respectively. Our EUV spectra have well-characterized uncertainties and could be used to inform exoplanet atmosphere models and population statistics. We are working on a way to infer the EUV spectrum for almost any exoplanet host purely as a function of its effective temperature and stellar activity. Talk to me if you have questions about the method, how you can use our spectra, or stellar EUV in general. Hope we have a good conference.
Hi, my name is Hannah Diamond Lowe. I'm presenting the high energy spectrum of the nearby planet hosting inactive mid-M dwarf LHS 3844. These results are out in a paper on the archive. The link is at the top of the poster. We are presenting the panchromatic spectrum of LHS 3844 with an emphasis on the high energy portion of the spectrum. We have observations in the UV from HST COS, observations in the X-ray from Swift XRT. We use these to also estimate portions of the high energy spectrum, which we cannot measure directly. A bit about how we put this spectrum together is presented in the poster. I also want to point out that we do observe a flare in the FUV. We actually extract this flare spectrum from the quiescent data. So we have both a flare and a quiescent version of the spectrum. All of the data are publicly available for download if you think this could be useful in your research. Thanks so much.
Hello everyone, my name is James Jackman and I'm a postdoc at Arizona State University working with Virginia Shikolnik. The UV emission from stellar flares has given them a potentially pivotal role in the habitability of rocky planets around low mass stars. Yet due to the difficulty of measuring UV flare rates for individual stars, current habitability studies often use white light flare rates measured with TESS to predict the UV flaring behavior, in turn relying on empirical flare models such as a 9000 Kelvin blackbody spectrum. The accuracy of these UV predictions have not been observationally constrained. So to this end, we have combined TESS short cadence observations with archival Galax light curves, made using the G-photon tool to test the UV predictions of white light flare and habitability studies. Our current results suggest that such studies can underestimate the near UV flare activity by up to a factor of 5, and we are currently working on expanding this analysis to the far UV. Please come and chat to me by my poster if you would like to know more.
Hi, my name's Kevin Moore. I'm a third-year PhD student at McGill, and my poster is about the habitability of Earth-like planets orbiting M-dwarf stars, which we refer to as M-Earths. Due to the high levels of X-ray and ultraviolet radiation emitted by the host star, water loss to space can completely desiccate the surface. Our hypothesis is that we can hide water in the mantle and degas it to rehydrate a desiccated surface once loss rates diminish. We test our hypothesis using a coupled model of the deep water cycle and parameterize loss of space from the surface for simplicity. Our simulation results support our hypothesis, but are strongly dependent on the tested loss rates and the XUV timescales. Because of the importance of loss, we are in the process of directly modeling the atmospheric loss rate using M-dwarf evolution models and a 1D atmosphere. Thank you for listening, and I'd be happy to answer any questions.
Alrighty, that is it for poster pops today. So let's give everyone a big round of applause for our poster pop presenters yesterday and today. And like Evgenia mentioned, these are on sort of continuous loop in GatherTown. If you go to the poster hall and then the bottom right-hand corner, there's a TV and you can go back and rewatch any of these and also go visit their posters.
Awesome. Thank you, Melody, for stitching those together and everyone for sending in their poster pops. We are perfectly on time with a 15-minute break. So we'll be back at 10:50 for the next session on exoplanet observations, as well as upcoming missions in order to achieve our dream observations. So we'll see you all soon. Have a nice break. All right, Safar, are you here?
Yep, hello.
Oh, hi.
Hey.
Thank you so much for chairing.
Yeah, my pleasure.
Let's give folks one more minute to come back and then we'll get started. Do we have all our speakers? Let's see. All right, shall we get started then?
I'm ready.
You ready? Antonia, are you ready?
I'm ready. Can you hear me?
Yep.
Okay, great.
Hey everyone, I just wanted to introduce to you our speaker today, Antonia Oklopcic, who will be talking about the importance of UV radiation for observations of escaping exoplanet atmospheres. Take it away.
Okay, I'll share my screen. Can you see the full screen presentation? Okay, great, thank you. Yeah, and big thank you to the organizers for this fantastic meeting and the opportunity to give this talk. So it has already been mentioned in previous talks today that atmospheric escape is very important for the evolution of individual exoplanets, but we also see imprints of atmospheric escape in properties of entire populations. So it has already been discussed that the hot Neptune desert or the radius gap have been linked to atmospheric escape. So definitely one way to learn about the physics of atmospheric escape is to study these long-term effects of this process on the entire population. But another way is to zoom in on individual systems and try to observe atmospheric escape in action as it happens, and then use these observations to try to actually measure the mass loss rates and then link them to link those mass loss rates to various properties of the system, such as the planet mass, radius, incident flux, and learn about atmospheric escape in that way. And so this is the approach that I'm taking in my work. And so the way we can observe atmospheric escape is through transmission spectroscopy. And we have heard already a few times today that the hydrogen Lyman-alpha line is an excellent probe of atmospheric escape. And in fact, it was the first, this is how the first evidence of atmospheric escape was found almost 20 years ago. So we've seen these plots a few times today already, so I'll just quickly recap. The basic idea is that if we look at for example, the light curve, transit light curve in the hydrogen Lyman-alpha line, the transit depth is many, many times larger than the transit depth of the broadband optical transit. And this is telling us that this cloud of hydrogen extends very far out from the planet and blocks a significant fraction of the stellar disk. It has also been mentioned that we can use other UV lines, so UV lines of metals, to basically make similar observations. So this is a plot from Singh et al. Showing detections of magnesium and iron ions, absorption lines that the transit depth extends basically beyond the Roche radius of the system, which is an indication that this gas that is causing this absorption is no longer gravitationally bound to the planet. And so these observations have been great, have been really the smoking gun evidence of atmospheric escape in action, but already a few people have mentioned that there are also challenges with observing these UV lines. So a lot of many exoplanet host stars are intrinsically quite faint in the UV. And also with hydrogen Lyman-alpha, there's the problem of the line core being absorbed by the ISM. So in recent years, another probe has been found to be, another line has been found to be an excellent probe of these upper atmospheres and atmospheric escape, and that is the helium 1083 nanometer line. So two great things about this line is that stars are typically much brighter, are typically quite bright at 1 micron, so we can get a lot of photons to work with. And another great thing is that this line is accessible for ground-based observations. So there are many telescopes at our disposal that can do this type of observations. And as a result, in the last 3 years, we already have more detections of these extended atmospheres in the helium line than in all these UV tracers in the last 15 or 20 years. So, and that's just because it's so much more observationally accessible. But this line also has a really interesting physical origin. So unlike the hydrogen Lyman-alpha line, which originates from the ground state of the hydrogen atom, this helium line originates from an excited state of helium. So this is this 2,3s state, which is radiatively decoupled from the helium ground state, which means that when a helium atom is excited into this state, it kind of just sits there and lingers for a while, which is great because it means that a large population of atoms can build up in this state and then cause absorption from this state. And the strongest line is this 1083 nanometer line, which is this transition over here. But when we do a really careful calculation of level populations in an extended atmosphere of an exoplanet, we find that typically only less than 1 in a million of helium atoms is actually in this excited state. But fortunately, in gas-rich exoplanets, there's so much helium that cumulatively enough column density is produced in this line that we can observe transit absorption depth of even a few %, as has been seen in some of these planets. And just to quickly want to note this new result that has recently been submitted. This is work led by Jessica Spake and in collaboration with Lynn Hillenbrand. So we looked at WASP 107b, which is actually the first exoplanet that has in which helium has been detected by Jessica Spake in 2018. And so we got this KIC NIRSPEC spectra, and we got a really good post-transit coverage. And we see this extended, when we look at the light curve in the helium line, we see this extended basically tail of helium. We see evidence of absorption extending almost 2 hours after the end of the optical transit, broadband transit. And just using simple geometrical arguments, this tells us that there's helium extending out to about 7 planet radii. And similar tails have been seen in a few other systems in helium, so WASP 69 and HD 189. So these are not as extended as in what tails that we see in hydrogen Lyman-alpha, but still we do see some symmetry in light curves in helium as well. So the basic goal of all this work is to translate these observables, so the transit depth and the light curve shape, into actual properties of escaping atmospheres, and primarily the mass loss rate. But it's important to keep in mind that these observables depend on these various, what I call here, macrophysical properties, such as the mass loss rate of the planet, also the stellar wind, because we see that this outflow is shaped by the interaction with the stellar wind. So this will affect the light curve and the shape of the light curve. But it's important to keep in mind that the actual transit depth that we see also depends on the what I call here microphysics, and that is the relative abundance of this excited helium in the outflow. So it's not only necessary to have the outflow, but we also need to have enough of this helium excitation in order to see anything. And this is where UV radiation again comes into play. So even though we try to kind of avoid all the difficulties with UV by moving into near infrared, still UV comes back as an important player even for helium, because when we look at the main mechanism that populates this excited helium state, it's actually photoionization followed by recombination, because this excited states is almost 20 electron volts above the ground state. So in planetary atmospheres, typically we don't expect the state to be collisionally excited. Most of excitation happens through this so-called PR mechanism. So for this mechanism to work, we need a lot of extreme UV photons, so photons around 500 angstroms that are energetic enough to excite ground state helium. And so basically, as a simple kind of rule that you might expect that, if we have higher EUV flux, then we expect to see more excited helium atoms. And to first order, that really works. So in this study from a couple of years ago, I just performed a very, very simplistic experiment where I kept this model atmosphere exactly the same. The only thing I changed is just the UV flux, or basically this translates to the distance from the star. And you see that the fraction of helium atoms that are in this excited state that is responsible for producing this absorption line increases as you move closer and closer to the star. And this is kind of supported by observations. So several authors have made versions of this plot, as shown here from Casper et al., where they plotted detections of helium or non-detections with these arrows as upper limits as a function of XUV flux. And in general, we see the trend that we tend to see helium in systems that have higher extreme UV flux. And then in these that have lower UV flux, we only get the upper limits. But that's only part of the story, because we also need to look into what mechanisms depopulate this excited metastable state. And in certain conditions, the main depopulation mechanism is direct photoionization from this state. And to ionize this metastable state, we need photons also in the UV, but at slightly longer wavelengths, around 2600 angstrom. So it's basically the balance of radiation between these two bands that sets the population level of this excited state. So it's not enough to only have really high extreme UV. We also would like to have low values of this mid UV flux. So basically try to have a balanced or a hard spectrum. And when we look at different spectral types, it turns out that kind of the sweet spot, the best ideal spectral shape we find in K stars. And then again, when we go back to this plot from Casper et al., if we look at what are the actual spectral types of these of each of these systems, we see that most detections so far did actually occur around K-type stars. Not, of course, all of them. So this is, I mean, this doesn't mean that we don't at all expect to see helium in planets around other types of stars. This just means that ideal conditions in terms of this photoionization balance are met around K stars. So basically, the gist of the story is that the stellar EUV is really crucial for excitation of helium. So when we want to model our signals, we really need to have a good input spectrum in the stellar EUV wavelength range. And this is starting to be one of the big limiting factors in how well we can model helium absorption and how well we can translate observations into quantities that we care about, such as mass loss rates. Because here I show in this example that, of course, we cannot directly measure extreme UV for most exoplanet host stars. So people do UV reconstructions. And there are different ways to do that. And there are experts in the audience who know about this much more than I do. But not all reconstruction methods necessarily agree with each other. So here I took two different reconstructions for the same star from this paper from Buria et al. 2018, and thank you, and try to model a helium absorption, and we see quite a large difference in the model prediction. And this is definitely, observationally, we would be able to distinguish between these two cases, but as an input to our models, we're not sure which model to use. So this is becoming a limiting factor in how well we can interpret our observations. But there might be a way around this, or because for all transit observations that we make, we observe transits for a few hours, but we also observe the star itself for a few hours. And now we have a lot of really high quality, high resolution spectra of stars in the helium line. And so the same mechanism that is responsible for populating helium in the planetary atmosphere also populates helium in the stellar chromosphere and produces the stellar helium line. And so people have known this for a long time, for the sun especially, that the helium absorption is correlated with EUV emission. And we can see this in these resolved images of the sun, that these active regions that have strong helium absorption are also regions of strong EUV emission. And people have recently started taking these deep learning approaches to try to predict solar EUV from the helium absorption. And what I'm going to argue is that we can use resolved, even not resolved images of distant stars, so just the integrated spectra, to actually say something about the distribution of these active regions on the stellar surface. So one really convenient thing about the helium line is that it consists of, it's a triplet, so 3 lines. So when the strong component that is a blend of these 2 lines becomes optically thick, this weak component is still optically thin and keeps growing even when this strong line already saturates. So basically, if we can measure the strength of this line and the line ratio, we have a way of breaking the degeneracy between optical depth and the filling factor of the region that is responsible for the helium absorption. And so we did that analysis for WASP-43. This is again work done with Lynn Hillenbrett and Jessica Spake. So we obtained a really nice spectrum of WASP-43 and tried to disentangle this kind of optical depth versus area. And what we find is that if we assume that the surface is covered in 2 components, one that does contribute to helium and one that does not, we get that the filling factor of the contributing area component is about 30%. So about 30% of the star contributes to the helium absorption, and it has an optical depth of about 1.5. And this is really helpful when we try to also model transit itself, because we may see some small variation in the transit depth as the planet crosses across these inhomogeneities. But if we look at the sun, and I'll just quickly finish up here, when people look at resolved regions of the solar surface, we see that different portions of the solar disk, such as active regions or coronal holes or quiet sun, they really live in different parts of the parameter space of the helium line depth versus line width on the line offset. And the question that I wanted to ask is, well, how good our stellar spectra need to be for us to really be able to tease out all these different components? So basically, how can we take just an integrated spectrum and say, what is the covering fraction of these active regions versus coronal holes, which will tell us something about, fast winds? And it turns out that this might be possible, but we just need really quite high quality spectra, so high resolutions, about 100,000, and signal to noise ratios higher than a few thousand, so maybe 10,000 ideally. So this is something that's just slightly beyond our reach for now, but hopefully for the future. And so I think I'm out of time, so I will just quickly summarize here that UV radiation is crucial for direct observations of atmospheric escapes, whether we're looking at actual UV lines, such as Lyman-alpha or metal lines, or even if when we move to near infrared in the helium line, extreme UV spectra is still crucial for our modeling, and we need to understand it. Thank you for your attention.
Thank you, Antonia. So we have time for one question. And if no one has a question, I actually have a question. Chair's prerogative. I was wondering if there are any targets that are, K-stars with planets that are close enough that we can get Lyman-alpha observation and a helium detection.
So I think there have been already, let me go back to this, sorry. So I think HD209 has both, HD189, GJ3470 I think has both. So yeah, I think there are a couple examples already that have both. Yeah.
Thank you very much. If anyone has questions, please direct them to the chat. Our next speaker is Josh Lothringer. We'll be talking about the importance of NUV opacity in extremely irradiated objects. Take it away, Josh.
Hi, everyone. Let me share my screen. Are you looking at the right one or the wrong one?
So I see both. Like
You
you present your next slide as well.
Is that? Sorry.
There you go.
Let's try this again. Display. Like this?
Yeah, perfect.
Okay, awesome. Yes. Okay. Hello, everybody. Hello again. I'm Josh Lothringer. I'm a postdoc at Johns Hopkins University. I think now is as good a time as any to share that I'll be moving to Utah Valley University to start as an assistant professor there. So you should come visit me at AAS in January, because that'll be in Salt Lake. So come say hi. So the topic of my talk is the importance of NUV opacity in extremely irradiated objects. And the reason I worded it like that was because I originally was going to talk about irradiated brown dwarfs on white dwarfs, because they experience so much ultraviolet opacity or ultraviolet irradiation. In fact, it's entirely dominated by the ultraviolet. And I have a paper from last year about that. So if you're interested, they're really interested objects, go check that out. But I want to focus today actually on ultra-hot Jupiters in particular. And so those are what I define as any Jovian planet above equilibrium temperature of like 2000 Kelvin. And the reason we care about them is because they're spectrally rich. So there's a ton of this laundry list of opacity sources and atoms and ions and molecules that we've been able to detect in the past like 4 years. It's been a really exciting time to be thinking about these planets because there's so much discovery going on. And one reason why that's happening is because they're just some of the best targets observationally. They're bright in thermal emission, they have inflated radii, they're short orbital periods, large scale heights, and less clouds. So these are the most spectrally rich planets we can characterize at this point, so we can probably get a very detailed understanding of their atmosphere. Or at least that's the goal. So like I said, there's many metals have been detected in these ultra-hot Jupiters. So this is an example of WASP-76b, again, one of the top targets of all exoplanets to look at the atmosphere. And so at high resolution, you can detect things like iron 1. You can actually resolve lines, and there's a number of works that have gone into that. And then at low resolution, you can also see the same signatures just at low resolution. So I'm showing the HST and Spitzer spectrum of WASP-76b in transit. You can get molecules at longer wavelengths, but at shorter wavelengths, we think this slope here at the shortest wavelengths is due to these same metal opacities that we measure at high spectral resolution. So there's kind of a complementary techniques here, which is really cool. But the question I want to ask is, what can we do with these metal detections? Just finding them is cool, but what can we actually find anything out about these planets? And I'm going to hopefully talk about 2 of these. So the first one is that the presence or absence of these metals as a function of planetary equilibrium temperature can reveal the details of cloud formation. And the second is that the abundance of these metals when compared to volatile elements can reveal information about the formation and migration histories of short period giant planets. So I'll start with the first one. So we got, here I'm showing a bunch of transit spectra. So RP over R star versus wavelength for a number of generic Jovian planet models from Phoenix. So at short wavelengths, you can see, especially for the hottest planets, a whole bunch of different lines that we can begin to characterize. So they kind of start to look like stars a little bit. You see all the atoms and ions you kind of expect to see in a hot star. But as you cool, as you go down here, down to 800 Kelvin, those metals slowly start to disappear. And the reason they start to disappear is because more of those elements are going into the condensation of different grains. So for example, if when magnesium and silicon oxide start to disappear, that would mean that those elements are going into the formation of magnesium silicates. And so this is one of the few ways that we can actually get at the composition of clouds. Empirically at least. So we have a theoretical understanding of when those clouds should form. And we can look in the infrared and see that the clouds are there, but to actually get an understanding of their composition empirically, we can use this to look at the short wavelength spectrum and when different metals are disappearing out of the spectrum. So one way you can think about this as well is with what we call transit depth colors or transit radius colors. So this is what I'm showing is as a function of equilibrium temperature, the transit radius difference at blue versus red wavelengths. And as you can see, the models kind of indicate a trend that you should see, that as you go to low equilibrium temperatures, the difference between your blue and red wavelength should kind of lessen. Rayleigh scattering will have a constant slope here that you can also detect. And I'm showing a bunch of STIS data that kind of shows something that's going on. It's kind of hard to tell. Some might be showing metal absorption, some might be showing Rayleigh scattering from haze and stuff. So I think we need to do two things. Look at more targets, especially UV bright targets, because not all these planets are necessarily around UV bright stars. So if you prioritize that, that'd be great. But we also look in the NUV. So the reason to go to the ultraviolet is that the features are just that much bigger. So this NUV to red color difference becomes like a 5 scale height difference between Rayleigh scattering and chemical equilibrium. And then at the shortest wavelengths, metals and the metals become more important than scattering. So at low equilibrium temperatures. So if you go to the NUV, this kind of becomes maybe a little bit more feasible and a more tractable problem. Okay, so that's the first thing. The second thing I want to talk about is that if we can go out and measure the abundance of these metals and compare them to volatiles, we can get information about the planet formation. And so this is kind of analogous to the idea that if we go and measure C to O ratio in a planet's atmosphere, we can use that as a tracer of its planet formation. That's tracing the ices in the outer disk that went into enriching the atmosphere. The same thing can apply to ultra-hot planets, but we can constrain the refractory abundances for the first time. We don't even have constraints on the refractory abundances in Jupiter and Saturn. We don't know what the rock to ice ratio is there. So this gives us a very first understanding of that kind of property in gas giants. And so you can imagine measuring a refractory to volatile ratio in an atmosphere, and we can map that to the composition of the planetesimals that went into enriching the planet. So you can get a rock to ice ratio of these ultra-hot Jupiters, or at least as indicated by the atmosphere. So we tried to go do that with WAS-121b. So I'm showing here the HST spectrum of WAS-121b. So at long wavelengths, we can detect water, which gives us a constraint on the oxygen. At short wavelengths, we get metals. So it looks a lot like WAS-76b, where the slope at short wavelengths is likely from metals that we've confirmed are there through high resolution observations. So with a retrieval, we can get a refractory to oxygen ratio of 5 plus or minus a few times solar, which you can turn into a rock to ice ratio of somewhere greater than 2/3. So all that goes to say is that a significant amount of rocky planetesimals had to enrich the atmosphere of WAS-121b during its formation or migration for us to be able to see all these metals at short wavelengths at high and low resolution. So that's pretty cool. But what's cooler is what we can do in the future. So with James Webb, we'll open up carbon as something we can constrain. So you get carbon to oxygen and refractory ratios in these ultra-hot Jupiters. Elemental abundances from high spectral resolution observations can open up individual refractory abundances, so we can get iron and magnesium to oxygen, stuff like that. And I also have a disclaimer here that this gets really complicated because interior physics, atmospheric escape, and 3D condensation all need further investigation and to be well understood to turn this into robust planet formation migration constraints. But with that, I'll leave you. I hope I've convinced you that ultra-hot Jupiters are high-value targets and that the metal-rich short-wavelength spectra of ultra-hot Jupiters provide unique opportunities to understand cloud formation and planet formation. So I'm happy to take any questions.
We have time for a couple questions. Sophia has her hand raised.
Yeah, I was interested in how well you think you understand the opacities of these metals in the NUV, because if you look at Phoenix model atmospheres compared to observed spectra, it's clear that we have unaccounted for opacity sources that are going to bias your results. So I wondered if the same thing is happening here and if it affects your ability to go from observed metal line strengths to estimates of the abundance.
Sure, yeah, I think that there's probably some uncertainty there. I know we understand the atomic opacities a lot better than some of the molecular opacities, things like CN or something that we might not understand as well. But I think just iron opacity we understand pretty well. There might be some things like NLTE effects that might be messing with population levels. So if turning them into abundances might be complicated. There's a lot of technicalities to go into turning detections in the atmosphere to abundances, but I think it's work that's tractable and important.
I have a quick question for Josh. So do you know if the high resolution STIS observations of metal lines, if they provide constraints on the abundances of those metals?
That's a fair question. I would hesitate because you're likely probing the non-hydrostatic atmosphere if you're looking in those line cores, because you're usually trying to probe atmospheric escape at that point. So I'd be a little bit leery. It might give you a good idea of whether they're there, and maybe if you look at a bunch of the weaker lines or something, then you'll be able to get something that probes the actual hydrostatic atmosphere and turn that into an abundance. Because that's what happened in WASP 121b, right? Is you found the ion at high resolution that's escaping, but at low resolution, you might be able to get a constraint.
Great, thanks, Josh. Our next speaker is Leah Corrales from the University of Michigan, and they'll be telling us about capturing exoplanet transits with Swift UVOT. Take it away.
Right, can you hear me? Great. I'm really excited to be here. This has been a really great conference so far, and I'm excited to talk to you about work that we're doing to capture exoplanet transits with Swift UVOT. So Swift is a telescope that was originally designed to study gamma ray bursts, but it has X-ray and UV capabilities that you can get simultaneous data on, and it has a rapid slew time and flexible schedule. So it's a small telescope that's not necessarily ideal, but it's definitely a great starter telescope for capturing NUV transits of exoplanets. And as has been mentioned before, in the UV, we can start to probe metal lines from an exosphere or an escaping atmosphere. And I just want to point to this work by Young et al. In 2020. They showed that when you include the effects of an exosphere in your planet transit measurements, when you look in the near UV, which is where we're probing with Swift, you can get these really deep iron 2 and magnesium 2 lines. So this is an R of 100,000 simulated spectrum, and you can see you can get a transit depth of 30% or more if you have extremely good resolution. And the SING result has already been mentioned, so I won't go into it in detail. But I just wanted to point to the first exoplanet transit ever measured with Swift, and that's WASP 121b, an ultra hot Jupiter with a pretty high estimated atmospheric escape rate. This work was done by Salz et al. In 2019. And they showed that they were able to measure this NUV transit, and it's about 35% deeper than the optical. And what they find is that if you extrapolate from the IR optical regime using Rayleigh scattering alone, that transit depth is much deeper than what you expect. So that's this difference here. This is their posterior distribution for the planet radius divided by the stellar radius. And you can see there's a big gap between what's predicted. And they do a few models and they point out this is probably due to excess absorption from iron 2. So this result gave me the confidence to try this out with Swift. And we did a study of 5 exoplanet transits with Swift. We basically selected our systems based on their possible observability. So we selected stars with NUV brightnesses on the order of 14 to 15 AV magnitudes and transit depths on the order of 1%. So these are hot Jupiters. And we do a few extra special things with our data analysis. So one of the steps that we did was actually try to calibrate our light curves by the light curves of stars in the nearby field in order to correct for any systematic instrumental stuff going on. That's something that hasn't been done before in the literature, to my knowledge. And we did some other things with binning that were slightly different from the Salz et al. Result. So we just wanted to convince ourselves that the analysis techniques work. So we reproduced the result for WASP 121b. So this is our light curve for WASP 121b. And another thing that we did is apply null hypothesis testing. So this on the right, these contours show several different things. So we basically fit our transits by fixing all of the parameters except for the planet radius versus the stellar radius, which is right here. And then we let the transit depth, the transit midpoint change a little bit because we weren't 100% certain about the timing and stuff of the telescope. So this delta T0 is just the difference in our fit between the predicted ephemeris value and then what we actually measure. So the blue contours show you the posterior distribution for these fits, the 1 and 2 sigma contours. The gray contours show you the results when we simulate data sets with similar scatter, same distribution of error bar sizes, just to see whether or not this is just a spurious fake thing. The other thing we do is we allow our RP over R star value to go negative, which is actually non-physical. So what that's actually doing is simulating an inverse transit. So it's just giving you the possibility that your transit light or your light curve in general can go up, not just down. So that's what those negative values mean. So using this technique, we show that this is actually a 5 sigma result. So we're pretty confident in the SOL's result as well as our own. For the rest of our transit measurements, it's not quite as good. This is actually the best transit that we have. It's XO3b, which is actually a really unique system. It's a hot super Jupiter, about 10 times the mass of Jupiter with a high eccentricity orbit. It's got a moderate temperature, so it's about 1800 K, and has a low estimated escape rate. And we actually measure quite a deep NUV radius. It's about 2 times the optical radius, or a transit depth that is 4 times the optical. We're estimating that this is about a 2 to 3 sigma transit based on what you see here. And it's potentially 18-minute early. Thank you, 2 minutes. So this is the rest of our results. So most of our other transits are quite marginal. So we treated this one as an upper limit, and these other 2 are basically non-detections. But I just want to point out that even for these upper limits and for these tentative transits, the transit depth is rather deep. So what we did is we divided the NUV planet radius by the optical radius, which basically cancels out the stellar radius uncertainties. And you can see that we do have a handful of, or a few transits that appear much deeper than expected. We also wanted to test a quick hypothesis kind of thrown out by the SOL's paper, which is, does this NUV transit depth correlate with escape rate? In other words, is this truly iron lines that we're probing that are likely probing escape, or is it something else? So we used our simultaneous Swift ArcStar-T data to measure the XUV, or estimate the XUV irradiation, and then estimate a photoevaporative mass loss rate for all of our targets. We also show one extra target from the literature, which is the King et al. Paper in 2018. And the most important thing to notice here is that, you know, we don't really have a consistent trend with estimated mass loss rate, and XO3b, which is our best transit so far, is very deep and has a very low mass loss rate because it's so massive. So it appears that it's not necessarily correlated with mass loss. And then the other thing I looked at was looking for any trends with equilibrium temperature. And we see a weird thing where, again, it's a little hard to say because this is all tentative and there's a lot of upper limits, but it appears that stuff above about 1700 Kelvin is deeper, and stuff below 1700 Kelvin is about on the order of 1 in terms of the NUV radius versus optical, or a little bit lower. And this reminded me of a trend that I've seen in the infrared, which was explained by clouds in this paper by Peter Gao in 2020. So just to describe this plot, the black line shows you the average grain size for clouds that are forming in planets of these different equilibrium temperatures. And this is the general pressure at which those clouds exist. I just want to point out that these models were evaluated for their near infrared obscuration. So this is definitely not the depth at which we're probing with the NUV. And the tentative explanation is that here at 1700, you get a break in the sense that most of the cloud particles are less than 1 micron in size. And I come from a background of studying particulates in the ISM, and I said right away, well, I would expect that when you have small cloud particles, which are predicted to be silicates in this temperature regime, you absorb or extinct a lot more UV light compared to the optical. So here we have like a factor of 4 nearly extinction efficiency in those types of silicate grains. Whereas when the grains get large, they're gray, so they extinct equally across the NUV and the optical. This is the transmission properties of the particular Swift filter we were using. And then there's a really weird case of WASP-80b. And here we sort of argue, because it's on the cusp between forming hazes, which form in the upper atmosphere, versus silicate clouds. So we make the case that, well, first of all, this is a different filter, and it's possible that, you know, the hazes are going to have a different absorption profile compared to these. So it could be that we're just missing the peak of the absorption from hazes in this particular system. It could also be stellar activity. And finally, I just want to point to a paper forthcoming from George King. They looked at hot Jupiter transits of HG 189733b. They have 18 transits measured with the UVW2 filter on XMM, the optical monitor, which is very similar to the instrument on Swift. And they get something that's basically consistent with about 1, which kind of fits into the paradigm that we're talking about here. But this is all very tentative. We are doing more transit studies to fill in this equilibrium temperature space. But overall, it looks like NUV transit depths can be significantly deeper. It's not necessarily correlated with mass loss rates. There's some other things we can imagine though. One thing I'd like to see is more exosphere atmospheric modeling, because we saw, as I showed in the Young paper, that the iron 2 features can get quite deep. And I'm just going to take a guess that there could be some tentative signatures of aerosols. And if you're not thinking about aerosols in the near UV or the UV in general, you should, because they really are quite absorptive. And we're working on developing more models for transit spectroscopy of the NUV, as well as just refining our observing strategies with Swift. So I'll leave it there. Thank you very much.
Thank you very much, Leah. Unfortunately, I don't think we have time for questions, but please do direct your questions to the chat. It looks like there's some spirited conversation going on there. Our next speaker is Kevin France. Title of the talk is Transforming Ultraviolet Spectroscopy of Stars and Planets in the Next 2 Decades, LUVOIR Ultraviolet Multi-Object Spectrograph, LUMOS. Take it away.
Thank you very much. I wanted to say thank you to Evgenia and the organizing committee for the invitation and for having this meeting, even though we can't be in person. So I'm going to tell you about the LUMOS instrument that was designed for the LUVOIR, the large mission that's being studied by the Decadal Survey, or evaluated by the Decadal Survey right now. I want to put a big asterisk on this, that this is a concept study. If we are so fortunate to be able to build a large UV optical flagship mission in the 2020s and 2030s, the instrument that we build will probably have capabilities that are similar to LUMOS, but may look a little bit different than what I present today. So kind of take this with a grain of salt for, let's talk about the capability and not the specifics. Okay. So I'm going to shift a little bit towards more rocky planets, as well as break into kind of some of the instrumentation mission part of this session. So, you know, in the UV, we don't really find our planets in the UV, but we make use of a lot of transit and radial velocity work to find planets in the habitable zone. And thanks to a lot of results recently, including from tests, we have a fair number of habitable zone candidates, or planet candidates now. We'll start the reconnaissance of these planets with JWST, hopefully, you know, starting the end of this year into next year. But of course, JWST doesn't really provide the stellar context that we get from ultraviolet observations. I'm not going to really talk about those contexts today. There are some nice talks scheduled for tomorrow on that. And the other thing I'll note is that a lot of the best targets for JWST are right at the edge of what HST is capable of, things like TRAPPIST-1 and GJ1214. So we really need something that's more capable than what we have currently to expand on the mid M dwarf and faint M dwarf capabilities that we've had with HST. So, but we're going to want a mission that can study the stars and also study habitable planets around all different types of stars, not just M stars. So we're going to need something different. And so that's where a mission like LUVOIR comes in. So I realized that I think I was the only talk that had LUVOIR in the title anyway. So I thought I would take a second and mention just kind of give a really quick overview of the LUVOIR concept. This is the Large UV Optical IR Surveyor. So LUVOIR is kind of like the super Hubble Space Telescope Swiss Army knives of space observatories. It kind of does everything. It finds the planets, takes spectra of the planets, and provides the stellar contexts. I'm going to focus mainly on the stellar contexts here and talk about the ultraviolet capability. But a quick reminder of what LUVOIR is in case you're not familiar. So this is one of the large missions that is being, like I said, reviewed by the Decadal Survey now. We studied 2 aperture sizes, a 15 meter large, and the 8 meter. This is covering far UV to near IR bandpass, imagers, and spectrographs. Think of Hubble, but very much on a grander scale. And the idea here is to try to be able to build a facility that is capable of answering the questions we haven't thought to ask yet. Remember, the L is for large. So this is the HST mirror compared to the JWST primary, compared to the LUVOIR A 15 meter primary mirror. So this thing is pretty big, and that's the little deployment movie down there. So just like HST and JWST, LUVOIR has a suite of instruments. And we use those to both find the planets, characterize the planets, and then also characterize their host stars. So we do the exo-Earth finding and the characterization using a coronagraph, so a starlight suppression technique. LUVOIR uses a coronagraph. This is a simulation for a solar system at 12.5 parsecs using the LUVOIR eclipse coronagraph. So you see there's the pale blue dot there. The inner working angle is driven by the observing wavelength and the diameter of the telescope and a bunch of other things, but those are the leading terms. So this is what we would see here. You'll see actually that Venus looks a little bit bluer than it is in real life. That's because it's working right at the inner edge of the inner working angle, so you get a little bit of refraction effects there. But we would find an Earth-like planet with the coronagraph, follow it for some fraction of its orbit to confirm that it is in fact a bound planet orbiting at about 1 AU equivalent distance, and then take spectra. So that's the hard part, and that's the part that I'm going to not spend any amount of time on. But then we would also like to have the ultraviolet capability, and that's where LUMOS comes in. So the rest of the talk, I want to give you a quick overview of the capabilities of LUMOS and talk about a few example science cases that are relevant to stars and planets in the UV. So LUMOS is a 100 nanometer to 1 micron imaging and spectroscopy instrument. I won't show you the video, the image of how big it is. It's several people tall. It has 3 primary modes. It has a low and medium resolution multi-object spectrograph. So when I say low and medium resolution, I mean resolving powers of about 500 to about 60,000. That multi-object spectrograph covers a 2x2 arc-minute field of view, so very comparable to what today's Hubble instruments do. Also has an FUV imaging instrument that is actually offset in the focal plane from the multi-object spectrograph, and has a slightly smaller field of view. And then something that's not shown, and I just show this this ray trace down here, not for you to read it all, but just to give you an idea about the ray trace complexity of what goes in here. Also has a high resolution point source spectrograph covering about 100 to 170 nanometers at resolving powers of 100,000 or 120,000. So let me talk a little bit more about the capability here. So this is an effective area plot. Now, effective area is not a one-to-one translation into sensitivity, but it's the leading term in most sensitivity calculations. So this shows the LUMOS A instrument compared to the HST COS instrument, which is the most sensitive UV spectrograph that we've flown so far. So it's pretty spectacular. It really is that, multiple order of magnitude jump that we would hope for from next flagship. So it has this kind of large effective area increase. But I also want to mention that it's not just effective area that defines your discovery space. Here are a list of the gratings. Don't read this whole table. The idea here is that to get a sense of the general resolving power from these medium resolution modes, which are of order 3 to 4 times higher than what we would have on, say, the Hubble COS M modes. So we're talking about a factor of 100 times the effective area, 3 times the spectral resolution, but also it's a multi-object spectrograph, and so we're able to observe up to 800 objects in every observation. So I kind of capture some of what's in this chart graphically here by showing a plot of the resolving power as a function of where in the detector focal plane your object would land. So of course, with optical distortions and stuff, we don't have a perfectly flat instrument response, but there are sweet spots where the resolving power is say maybe about 55,000, and then some lower resolution spots over towards the edge. Similarly, with the angular resolution, we go down to 20 some milliarc seconds, but somewhere on the edge of the field, it's more like 60 or 65. So I want to emphasize, though, that every one of these little individual apertures, this is assumed that we have a multi-object, a microshutter array that defines the multi-object aperture, sort of a souped up version of what we have on JWST. That we essentially, every one of them acts like a little long slit. So you're able to do imaging spectroscopy inside of all of those 800 shutters that you can observe simultaneously. So let me review. It's a factor of 100 in effective area, a factor of 3 in resolution, a factor of about 10 in angular resolution, and then many objects per field if your target field is dense enough. So it really, when you start, when you do the classic instrumentalists version of discovery space, the discovery space really is very broad compared to what we have with Hubble. Don't get me wrong, I love Hubble. You can't give a talk and say you don't like Hubble. Hubble's amazing, but this is really amazing. Okay, so let me take just a second to talk about just 2 relevant science examples. So one where we use the multi-object capability to, let's say, study young stars. Catherine and Christian and Will gave some nice talks yesterday about this. So let's zoom in on the nearest high mass star forming region, the Orion Nebula. So if you imagine that we have in this plot, in this corner, a 2x2 arc-minute field of view of the entire Lumos aperture. If we zoom in, just because you can't see everything there, zoom in, and this is 0.8 by 0.8 arc-minutes. Every one of these little red dots that I hope you can see on your screen is the actual projected size of one of those microshutter apertures. So we would then align with all of the known protostars in Orion, be able to take individual FUV spectra of all of those protostars simultaneously. We would then extract those and get a one-dimensional spectrum that if we were interested in, say, the raw materials for planet formation, like molecular hydrogen and water, we would see absorption spectra like this, looking through one of these little propylit objects. And we would do this for tens or, well, probably not more than many tens, several tens of objects per field. So with a couple of pointings in a target-rich region like the Orion Nebula, we would exceed all of the protostar spectroscopy that HST has done in its 31 years so far. So it's a pretty spectacular capability. The other example that I wanted to come to is something that everybody has talked about earlier talk about metal line absorptions from short period planets. So we've seen this GJ436b. Thank you to everybody who introduced this before. So it's very, very deep in Lyman-alpha, but no detection of metal species, probably because we just didn't have the sensitivity with existing instruments to do that. I'll mention that Ruth and Antonia both mentioned the importance of actually knowing the stellar EUV, that essentially all of these calculations depend on scaling relation assumptions of the stellar EUV. And so this is a separate talk, but James Mason is talking tomorrow about the ESCAPE SMEX mission, which is in phase A right now and is a direct EUV spectroscopy mission where we could actually measure the EUV spectra of many of these host stars directly, several hundred of them. So we don't have to rely on scaling relations. We do have something in the pipe that could measure these directly. Okay, that being said, that's my soapbox. So here is a simulation from Eric Lopez of what GJ436b's transit spectrum should look like in carbon-2, 1335, with the Lumos G150 mode. So it shows the thin histogram is the out of transit spectrum, the purple is the in transit spectrum, and then in the lower panel here is the light curve is a function of velocity. Now, this is spectacular because when we're in these excited ion lines, we're not limited by the opacity of the interstellar medium to detect the line center velocities. So we're able to, with an R of 50,000 spectrograph, get right down to the core of the primary species, not hydrogen directly, although we can measure the hydrogen wings like was talked about earlier, but things like ionized carbon, neutral oxygen, and probably several silicon species as well. So Eric and I took this one step further and put together a draft survey that one could do with Lumos to study atmospheric escape. And these are targets that were in the Tom Barclay's simulated catalog of test objects. So this work is 2 or 3 years old now, so we didn't have the full first cycle around results from tests. But essentially, these are all the objects that, all the colored objects are the ones where carbon-2 can be detected. And these are all the objects where we could have a 5 sigma detection of either carbon-2 or Lyman-alpha in a single transit. So no stacking. There's a lot of uncertainties about the inhomogeneities and the surface features in these UV ions. Essentially, you could put together a very comprehensive survey of metal absorption with a capability like this. Okay, so then in my last minute or two, I want to, I guess 1 minute, I want to mention that, none of these large mission studies, as exciting as they are what we call shovel ready today. So there's going to be technology development that needs to happen. And Shule is giving a nice talk later this afternoon on some of what we need for missions of all sizes, UV missions of all sizes, to prepare. I'll just talk about this stuff that I am more intimately familiar with very quickly. One of the things that the Lumos, or the entire LUVOIR observatory needs are these advanced lithium fluoride optical coatings. So we have a sounding rocket program at Colorado where we've worked with Goddard Space Flight Center and JPL to develop these coatings on large optics for the first time. So some of the results are a little bit mixed, but we have been actually able to demonstrate things that meet the LUVOIR goal. So this type of work, and I'm just sharing this because I'm familiar with it, but there's lots of stuff going on around the world to develop these different technologies. The other one that we are working on are these large format UV detectors. Lumos has a requirement for a number of 200 by 200 millimeter detectors. Those are 8 inches by 8 inch detectors. Those are enormous. And so we are actually working with the folks at UC Berkeley to test and fly some prototype devices that would meet these requirements. So, and then we, of course, package them all up in a prototype instrument, take it through instrument INT, demonstrate that the optical coatings are stable to typical INT and launch conditions. And then we of course, train students and stuff, which is another talk. Okay, so I think I'm about out of time, so I'll just go ahead and leave my LUVOIR summary here and take any questions you have. Thanks.
Thanks, Kevin.
That was great. Any questions? Oh, Leo, you have a question?
Yeah, hi, Kevin. Very quick questions. Are we going, first, is Lumos going to suffer from detector degradation like COS does? And my second question is, are we going to be allowed to point it to active M dwarfs?
So no, there have been a lot of advancements in atomic layer deposition processes for creating microchannel plates since then. So the current generation, like those detectors that I showed on the rocket, actually have a factor of 50 higher global count rate capability than what we have on Hubble today. So a lot of the things that have plagued us as observers for a long time will hopefully be less of an issue. Now that's offset somewhat by having a factor of 100 greater collecting area. So there is a consideration there. So that's really a question for the Space Telescope Science Institute, but the capability for high local and global count rates, much higher than what we have on HST today, definitely exist for these new detectors.
I have a quick question. Do you run up against saturation limits for nearby stars?
So in the far UV, the way that this is baselined is they're photon counting detectors. So as long as you don't overwhelm the ability to count the photons that are coming in, then you don't really, the readout time is not really a thing. There are also developments that I think Shirley will talk about for electron multiplying CCDs and CMOS arrays that will get around this problem with silicon detectors as well.
Great, well, thank you very much, Kevin. Looks like now we have a 15-minute break and we'll be back at 12:05 p.m. See you then.
Thank you, Zafar, for managing the show.
Oh, my pleasure. Thanks for having me. I think we can wait a minute for people to filter in. Erica, are you ready?
Yes, I am.
Cool. All right, everyone. It's my pleasure to introduce the next speaker, Erica Egan. They'll be talking about CUTE, moving towards flight readiness and atmospheric characterization. Take it away.
Great, thank you. So my name is Erica Egan. I'm at the University of Colorado in Boulder, and I work at the Laboratory for Atmospheric and Space Physics on a small satellite called the Colorado Ultraviolet Transit Experiment. So in this talk, I'll give you a small overview of the satellite and how we estimate it will perform once it launches later this year. So I'll start with all the pertinent information about the CUTE mission. CUTE was motivated by Hubble observations of inflated and escaping upper atmospheres of short period exoplanets, notably HD 209458 and WASP-12b. And while those observations showed that it was possible to study the upper atmospheric properties using NUV light, Hubble wasn't able to provide the time dedication necessary to study these dynamic systems. So CUTE was proposed as a dedicated CubeSat mission with a near ultraviolet band pass between 2,500 and 3,300 angstroms, which includes iron and magnesium features that we've seen on a couple of other NUV transit observations. And the instrument has a resolving power of roughly 2,000. So in the 1 year nominal mission lifetime, CUTE will provide roughly 10 to 12 transit observations of more than 10 short period exoplanets. Half of the orbital phase will be captured for each transit observation, and in-transit observations will be captured using a 5-minute observing cadence. And the satellite will launch in September of this year alongside the Landsat 9 mission as a rideshare. So CUTE, it is a 6U CubeSat, 6U spacecraft. The actual spacecraft body is roughly 10 by 20 by 30 centimeters, and the solar panels increase its largest dimension to about 90 centimeters. The telescope and the spectrograph occupy 4U of the spacecraft volume, and it's made of a rectangular Cassegrain telescope and a spectrograph mounted on the back of the primary mirror. There's a heat strap that's connected to the outer spacecraft radiator panel that serves as a thermal sink to keep the CCD cooled to reduce dark noise. The remaining 2U contains the avionics module, which includes a star tracker, sun sensors, radios, reaction wheels, batteries that are all part of the Blue Canyon Technologies XB1 package, and the instrument electronics, which are built by CUTE engineers. And then if you want to see more about the design or our testing process, you can see Fleming et al. 2018 in JADIS, or my paper Egan et al. 2020 in the Proceedings of SPY. So in order to measure how well the spectrograph performs, we used one of a vacuum calibration chamber within the Laboratory for Atmospheric and Space Physics facilities. And this chamber was historically used for sounding rockets, and we modified it to accommodate a CubeSat-sized telescope. So what you can see in the upper right is me and a researcher in our group, Ambali, and this is our first installation of the telescope into our launc tank. And in the middle and in the right pictures, you'll see us measuring the spectrograph and the telescope in 2 different orientations, and that was to account for a different gravity load that may or may not have affected the secondary mirror. And so we're happy to report that we didn't see any significant gravity sag on the secondary mirror. And then in the lower left, you can see one of our undergraduates, Jared Puseman, who made a lot of the machinery and mechanical mounts that are inside of the launc tank. So using this setup, we were able to focus the spectrograph and obtain a resolving power of roughly 2,000.
So I take that estimated resolving power and some other instrument characteristics like dark noise and read noise to see how sensitive Qt is to planetary transits. So what you're seeing here are basically the 1 sigma error bars folded over 6 transit observations as a function of planet and band pass. And on the x-axis, you'll see several of our main targets that we plan to observe during Qt's main mission. And on the y-axis, you'll see that 1 sigma bar transit sensitivity. So each colored dot references a band pass. And so for especially bright targets like Kelt 9 and Kelt 20, we're sensitive to less than 10% of the planet's radius. And then for dimmer targets, we'll be able to detect the transit in larger band passes, which means that we'll be able to constrain that rise in the NUV slope that was talked about in a few talks previously. So the majority of my days are spent in the lab to make sure that Qt will work and is ready for launch. And here's a basic flow chart of the mission readiness milestones. We're currently getting ready to subject the spacecraft to a vibrational test and test functionality and performance before and after the test. We'll spend the second half of this month of May in a thermal vacuum chamber to simulate the thermal environment of Qt's orbit and characterize any resulting systematics, as well as general spacecraft health and operation.
2 minutes.
So thank you. Finally, Qt has a large team of scientists and engineers that are helping to make it successful. Kevin France, who ended the last session before the break, is the PI of Qt. Brian Fleming is the instrument scientist, and I'm in the center here holding a scale model of the Qt telescope and spectrograph. And then all of those in the group picture are on Qt science team. Oh, sorry about that. A few of them, which are participating in this symposium. And then there are also several engineers that are pictured on the right. And this is just to say that there's a large team making this small satellite successful. So to recap, the Qt CubeSat is a 6U NUV spectrograph that will assess the upper atmospheric properties of short period planets. The mission will obtain several consecutive transits of more than 10 exoplanetary systems, vastly increasing the number of systems observed in the near ultraviolet bandpass. It's estimating resolving power of about 2000 will allow us to isolate spectral features like iron and magnesium. And then in the last 4 to 5 years since Qt was proposed and awarded, a lot of excellent and exciting science and observations have been added to the exoplanet atmosphere studies. And Qt sits in a really nice niche within the NEV transit spectroscopy realm. So with that, I will end and take any questions.
Any questions? So I was curious to know what the orbital period is and if it's a low Earth orbit CubeSat.
Yeah, Qt is a low Earth orbit, and it will have an orbital period between 90 and 100 minutes.
And I've heard before that Earth's escaping atmosphere can sometimes affect ultraviolet observations from space. Is that the case with Qt, or is that a different wavelength range?
That would be a different wavelength range. We don't expect any geochronal emission to happen within Qt's bandpass.
Cool, thank you. All right, well, if there are no more questions, please head to the chat. Our next speaker is Patricio Cubillos from the Austrian Academy of Sciences, and he will be speaking about the potential of NUV observations for exoplanet atmospheric characterization.
All right, I hope you can hear me and see my screen. Can you hear me? Hello?
Yes. Yeah, we hear you. We hear you great.
All right. All right, thanks. So we have seen already that UV observations are a great tool to characterize exoplanet atmospheres, particularly by looking at the upper layers of the atmosphere where we expect to see evidence of atmospheric escape. And we can see this just by looking, for example, at the distribution of exoplanet properties, for example, by looking at the Neptune desert or the radius gap, but also by looking at individual targets, in particular, looking at Lyman-alpha absorption during transit, where we can see an excess absorption which is caused by an envelope of hydrogen escaping the planets. So now moving on more into the near UV, the first of the observations actually they date back to some 10 years ago, when Vidal-Mayer reported on 3 HST transits of the hot Jupiter HD 209458b. And they focused mainly on the magnesium lines, where they found a detection of the neutral magnesium, but not ionized magnesium. And this was a bit controversial at the moment because according to the theoretical models, if there is any magnesium in the upper atmosphere, then most of it should be in ionized form. So this was one of the reasons for us to go back and reanalyze the data. And also by realizing that in this wavelength range, we should expect to see many more other metallic absorption lines. So here we can see our transmission spectra for the planet. In gray, you can see with the error bars, you can see the observations. In red, you see a non-LTE model of the planet. And then at the top, you can see the location of the main absorption features from the metals in this wavelength range. So the first thing we noticed was that we have a non-detection of magnesium, neither neutral nor ionized, which in a way it solves the previous controversy. And also we know of another independent reanalysis of these magnesium lines, which agree with our non-detection. But maybe the most important thing is that we saw several lines, absorption lines, that are consistent with the location of iron 2 lines. So now we are in this situation where we have iron 2 absorption in the upper atmosphere of this planet, but not magnesium. So the idea that we tried to propose in our paper to explain this was that the planet is actually in a hydrodynamic blow-off regime, where the hydrogen is flowing up from the lower layers of the atmosphere, and that is going to drag the heavier particles. And then at some level in the atmosphere, the temperature profile is going to cross the condensation curves for different species, and that is going to sequester mostly then the magnesium in the atmosphere, but not the iron. And so this idea is supported by this paper from Peter Gao from last year on nucleation theory that says that at these temperatures, most of the clouds are going to form primarily from magnesium and not from iron. And also from optical and near-infrared observations, we see that the retrievals, they require some level of cloud coverage on the planet. So I think this is the most important thing and the most valuable thing from near UV observations, which is when you put it in context with the observations from the lower atmosphere, and also with the theory of the dynamics and the chemistry, then we can make a much better we can have a much better global understanding of the physics on these atmospheres. So that was HD 209. At about the same time, we also saw a report on the near UV observations of WASP 121b. This is a much hotter exoplanet with an equilibrium temperature above 2000 Kelvin. So for this planet, these people, they found a detection of both iron and magnesium ionized, which is a slightly different picture than what we found for HD 209. So again, we can use this to constrain the lower atmosphere of the planet. In this case, what we require is that the temperature profile to be high enough such that it never crosses the condensation curves of this species, so that iron and magnesium can reach the upper layers of the atmosphere. So now we have two metallic detections in the near UV. We also got some time for the to observe near UV transits of HD 189. This is a much cooler planet, and it orbits K2 star, which is active. And that actually produces a lot of troubles in trying to analyze the data. For example, we see strong systematics that change with wavelength, and it doesn't seem to change to correlate with any known property of the instrument. So it has been a really complicated to analyze this data. And also you can see the activity of the star when you look at the transits at different epochs, where we see an offset in the transit depth depending on the moment where you observe the planet. And this can be attributed to contamination by spots or faculae on the star, which can be corrected at some level, but it needs to be revised very carefully. So this is our high resolution spectrum of the planet, and this is very preliminary, and we need to do much more analysis to confirm all of this. But at this point, we see non-detection of magnesium, neither neutron nor ionized. And we maybe see some absorption features of iron. But again, we need to double check that this is not noise, and also that the line intensities are consistent. But this is the picture that we have now for HD 189. But maybe to end with a more positive note, like Josh said before, maybe one of the greatest opportunities from the UV is to observe at ultra-hot Jupiters, because extreme irradiation leads to very strong absorption features. And this is one of the studies, for example, that we can do with ultra-hot Jupiters. This is led by Luca Fossati, where we were able to model self-consistently the population levels and the temperature profile of Kelt-9. And we have seen that when we do not assume an empty atmosphere, actually the temperature that we find for the planet is much higher than what you expect from LTE. And this is going to have consequences on the transmission spectrum. And we actually, with this, we found a much better fit to the observations of the H-alpha and H-beta absorption line profiles. So I'm just going to leave you with the conclusions, and thank you for your time.
That was great. Questions? I have a quick question.
Mm-hmm.
What if one were to stack together all of the absorption lines and then sort of create like a super sampled PSF for everywhere where you expect an absorption line? Do you think that could give you a resolution that's high enough to get any kind of velocity sensitivity?
Yeah, that's more or less what we do, what people do when you do a cross correlation. Essentially, you are combining the information from all of the lines, even if you don't see them directly. You are combining all of the data into one single, property.
Great. Well, if there are any questions, please leave them in the chat. So next up, we have Mark Swain from JPL. And the title of his talk is UV Scope, a mid-X mission concept for the ultraviolet spectroscopic characterization of planets and their environments. Take it away, Mark.
All right. 1 second here. Okay. So first of all, it's really a pleasure to be here today to tell you about the UV Scope mission, and what a great venue this conference is to do that. So UV Scope is a mid-X mission concept that is aimed at characterizing stars and exoplanets with broad ultraviolet spectral coverage. The PI of this mission is Evgenia Skolnick, And at the end of this talk, I'll also be introducing the rest of the science team as well. But if there are any follow-on questions that we don't have time to address after the talk, please follow up with either myself or Evgenia or other members of the science team. You're going to find a really passionate group of people about this mission. So UV scope addresses some of the biggest questions that we have today. These are questions like how do planets form, how do they evolve, and what are they made of? Of course, this is all building towards questions like, eventually looking for life outside of our own solar system to answer one of the fundamental questions of humankind, which is, are we alone in the universe? So UV scope really provides critical information for this, but as some of our previous speakers have also discussed, a mission like UV scope also is going to be highly complementary to exoplanet observations with James Webb and later on with the Ariel transiting survey mission. So UV scope really has a big role potentially both in exoplanets and in also providing an ultraviolet capability in the post-Hubble era that will serve the community. Now, one of the things that we like to show in the, to kind of illustrate sort of the scope of the UV scope science, no pun intended, is the graphic I'm showing here, and talk about the different regions of planet atmospheres and how that relates to the star and how what UV scope's role is in understanding all that. So at the outer layer, we have the exosphere. So we'll, for the purposes of this discussion, call that pressures less than a nanobar. There's already been a wonderful detailed talk about that by James Owens. But this is the region of planetary atmospheres where there can be ongoing loss. And as we know, understanding in detail atmospheric loss and escape is absolutely critical to understanding how planets evolve, both in the evolutionary sense and really understanding the context of small planets. And I can't stress enough how really important understanding atmospheric loss is as we study small planets. And so UV scope's study of atmospheric loss has a very important role in calibrating our understanding and making that quantitative. The second region of the atmosphere, which we call the upper atmosphere, extends from about a millibar to about a nanobar. This is a region where some of the condensates we've been seeing are talked about, seeing presented come from. It's the region that it's the region of the atmosphere that is feeding the part of the exosphere where ongoing escape may be happening. This is a region that UV scope probes with far UV and near UV observations. And it plays a fundamental role in completing transit spectroscopy in those wavelengths, plays a fundamental role in completing our picture that we'll have in transit studies with James Webb and Ariel. And finally, there's the lower atmosphere, which for purposes of this discussion, we'll call pressures greater than a millibar. And the role of the ultraviolet in the lower atmosphere is very important for establishing essentially the chemical reaction networks of the atmosphere and the photochemistry, which can profoundly, in some cases, change the atmospheric composition and chemistry. One of the ways in which UV scope would help understand this is by detailed studies of exoplanet host stars and other stars to understand the flare frequency distribution, and some of the time-dependent UV, which may in fact have a very important role in establishing atmospheric composition. Now, the first two studies, or the first two science cases of UV scope, involve transiting planets, either measurements of Lyman-alpha transits or measurements of UV continuum transits. UV scope will target about 250 transiting planets. Some of those are known, some of those will come from tests, and you see a notional graphic illustrating that transmission spectra here. The types of spectra that we'll get back from UV scope are shown here. So UV scope has a spectral coverage from about 400 nanometers to Lyman-alpha, really giving access to many different diagnostics which are, have a wide variety of science questions that can be answered, but also support these three fundamental science cases that UV scope will investigate. And I'll close with an introduction to our science team. Again, reach out to anybody on the science team if you have any questions. This is a very exciting mission concept, and I know that the rest of the science team is very enthusiastic as well. I'd be happy to stop here and take your questions. Thank you.
Questions? I have a quick question. What kind of orbit would it be in?
L2 is a very good place, and so that's what we're baselining for this.
Great. And do you think you'd have sensitivity to asymmetric transit morphology?
Oh, absolutely.
Great. And Ruth will convince you to look 6 hours early and 6 hours late?
Absolutely. Absolutely. Yes.
Oh wait, I have a quick question. Sorry, I didn't raise my hand, but I'm going to ask. Is it going to be able to do long-term observations, or is it going to be occulted by the Earth, just like the Hubble Space Telescope? Sorry if you already answered that before, but
Sure. No, this by observing at L2, UV scope has the ability to stare at a target for, in principle, quite a long time. So the detailed design of the mission, I wouldn't say is done yet, but I think we could expect to be able to have time on a given target, which could potentially be several weeks. Yeah, so I think a couple of months is probably possible with the current architecture, if that were desired.
Mm-hmm. There's a question from Girish.
Hello. I was wondering, for the post-Hubble prospects, what's the expected lifetime for them? Do you expect an extended mission, and how extended do you think you could get?
Well, certainly planning for an extended mission possibility is an important part of UV scope. I think it'd be a little premature to commit to specifics on what that might look like. Within the Explorer program, missions are generally aimed at a fairly bounded duration in time, which is sort of on the 2 to 3 year timescale. And then if there are opportunities and it is scientifically justifiable for an extended mission, then that is something that can be essentially applied for, and it's a competitive process. But it would be the UV Scopes team intention for the mission to be competitive for that kind of scenario.
Thanks.
I have a second question. Do you think UV scope will be sensitive to optical reflected light?
Optical.
Or sorry, not just in general. Will it be sensitive to reflected light observations and maybe optical phase and UV phase curves?
I don't know that we've had a chance to look at that. So that depends quite a bit on the albedo assumptions, of course. And I don't know that on the science team had a chance to look at what the albedo assumptions would be. In principle, if you had a planet with high albedo orbiting close to a star that had strong UV emission, I suppose it's possible that's conceivable. That's an interesting question. I think that's something we should look at.
Great. Well, thank you very much, Mark. Remaining questions can go in the chat. Ellen, she's our next speaker now. So our next speaker is Shulay Nigzad, who is at JPL, and her talk will be about enabling technologies for future ultraviolet and ultraviolet optical missions. Thank you very much.
Thank you. And good afternoon, everyone. Can you hear me okay? Great. So it is a true pleasure to be here, both to hear all these great talks about everything ultraviolet, and also to get a chance to tell you about the work we are doing on some relevant technologies. I was pretty ambitious when I was talking to Evgenia and set up this title, but just to orient ourselves, my talk is going to be focused on detectors and a little bit about coatings as well, but mainly detectors. So we've had a really nice set of talks talking about the powerful diagnostic elements in ultraviolet. We've talked about even some issues with detection, what we desire to have for future in detection. For example, a dynamic range was mentioned, photon counting has been mentioned. And here I'm just showing from Rosetta data, pictorially what we mean with desiring to improve the dynamic range when you have faint objects and brighter objects to be detected in one sweep. You can already see what the issue might be. We've talked about photon counting. We've also not so much described what the case might be when you're not photon starved and maybe you have a lot of high energy photons impinging on your detector and maybe causing damage, as this is showing from the SOHO detector, that actually the damage caused the reduction in sensitivity. The cornerstone of a lot of UV detection is, of course, photon counting, and many of us in the UV community are very familiar with the fact that image-to-based technology of microchannel plates have been the workhorse of detectors in these instruments, And they have some really nice features that have made them the mainstay of detection. They are photon counters, and they have red rejection. And despite some of their shortcomings, they have been used for many decades. So what we are talking about here today is trying to use silicon for ultraviolet detection. And we've already seen from the time of Kepler, large focal plane arrays being populated with very high quality silicon detectors, ground-based observatories, as well as some space-based observatories are being populated by these nice detectors. Most of it we're talking about in the visible. Now we're trying to push that into the ultraviolet. So why the interest, in addition to the fact that they are ubiquitous presence in the imaging? I'm already talking with you using a silicon imager in this communication. We have starting material, which is cheap, manufacturing or fabrication of it is mature. They're very linear, scalable, and they also are available in various readout schemes. There's CMOS, CCD, hybrid. In fact, Perseverance just flew a whole number of CMOS cameras, OCO3 context camera before that. These are some of the first CMOS cameras that NASA has flown, and they're engineering cameras, but there's a poster, for example, in this symposium about Duet that has baselined actually a 2D doped CMOS detector. And of course, as I will show later on, LUVOIR and bigger missions in the future are baselining these detectors. And there are, of course, features of CCDs as well that are special and available in silicon. So the talk will be focusing on using delta doped silicon detectors with custom atomic layer deposition or ALD coatings to address this high quantum efficiency, high dynamic range that was addressed while still doing photon counting, having red rejection, which is a big deal because, again, we are seeing in the visible, looking at each other in the visible, cutting the visible out of silicon and boosting the UV, it's a big deal. That's what we are going to be addressing. And also you're in space for UV, so radiation tolerance is important, and that comes from both the 2D doping as well as some of the readout schemes, as well as you want it to be reliable and have photometric stability. So just very, very quickly, what is 2D doping and why you should care about that? delta doping, or more general term, two-dimensional doping, is a process that turns essentially any type of silicon detector into a high efficiency UV detector. You're looking at the cross section of a silicon detector that in this case is a CCD readout, but this pixel structure, the readout could be anything, could be CMOS, hybrid, a special CCD. Photons in a back illuminated come from the back where the pixel structure is not there and it's just pure silicon. And we put a very high quality single crystal silicon, very, very thin, but we put so much charge in it that the fields near the surface are changed, so that instead of traps for photoelectrons near the surface, you will have now a field that will send them toward the readout. And why it's important to take control of near the surface is because UV photons are absorbed very in the first 10 nanometer of silicon, first tens of nanometer of silicon. And so it's very important to take control of the fields. So you put a lot of charge affects the field, and then you could see these. And because again, it's silicon is compatible with any type of silicon detector. And why you should care is really in the performance. Here I'm showing a couple of quantum efficiency plots. On the left, you're looking from extreme UV to the visible data points matching the 1 - R of silicon, essentially showing that your only loss is reflection. So you have now managed to get rid of any losses of photoelectrons. And then if you could now tailor the absorption, control the absorption of photons, then you can have a tailorable detector with very high efficiency. On the right, I'm showing in the Galax band, really, something that Chris Martin had given us a challenge, a set of detectors that for different spectral bands have been optimized to have quantum efficiency above 50%. These are delta dope detectors, delta dope CCDs. One of them is an electron multiplying CCD that have really single layer anti-reflection coatings. Most of them are with ALD, and that's important because when you're in the UV, layers have to be very thin, so you want to have really nice controls, stoichiometric, very nicely uniformly and no pinhole type of layers, and ALD can give you that. I mentioned that it is applicable to all sorts of devices. So in addition to performance, you could get the different readout. Here is, I'm showing the application of a 2D doping or delta doping to CMOS of the flavor of the Europa Clipper ice. We are actually a backup for that. And that's the range that they gave us. So if you want broadband, you go from near UV to somewhere near infrared. And the reason the QE is low here because this device is thin. So if you want higher efficiency, you go with thicker devices, as we did here with the thick STA devices. As you can see, we can tailor this band from near UV to near IR. And these devices are actually two flavors of them are at Palomar, WASP, and ZTF. So I mentioned photon counting. Now, how do we do photon counting in silicon? That's taking advantage of one of the features of CCDs, which are serial readout devices. So charged photoelectrons are really transferred down the length of the device and read out, transferred through a serial register and read out through a single amplifier. Now, if you add another serial register in which you add enough of it, higher voltage clocking, so that you have a probability of getting impact ionization, you can increase your signal to noise so that your signal is boosted so much you can threshold the read noise and get high signal to noise and potentially get a photon counting. The nice thing about EMCCDs is that you can also address the dynamic range because you don't have to always go through the EM. You could turn it off or turn it on. So it's a pretty nice thing. And we have